Testing, 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 testing. SAS, 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 SAS. Testing, testing. We're good?
Can you try to be a bit more close to the mic?
Sure.
Well, let's see if it works now. Can you just...
Sure.
Can you just test if the mic works?
Yes, it works.
Testing.
Testing.
Good enough?
Yeah. Maybe it's not so loud. Come again?
Again? Or I can speak louder?
Yes.
Or can you try this one instead? See if this works.
All right.
So it's just the volume.
I've given a talk in which I put it outside and then it fell in the middle of the talk. So put it below your shirt. Okay. All right, testing again.
I think it's a little bit better when it's a little
Again, like that.
It doesn't work very well.
Testing, testing. Otherwise, I can hold the microphone in my hand.
Is that okay?
Well, sure.
I think that works better.
Okay. Whatever works. Okay, so you want it back?
Ah.
No, I know the sound is better, but restrict my freedom of movement. So testing, 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 testing. Looks like it's not on mute. Testing, testing. More volume, baby. Okay, then I can speak really loud.
That's what I mean.
Oh, hi. Yeah.
Good, thank you so much. What about the screen?
It seems like the screen is not.
You need to intervene. Full screen, please. I mean, presentation mode. There we go. Super. Thank you so much. Yay.
So our first keynote speaker is Professor Olivia Denvy. As you know, Professor Denvy is renowned for many foundational contributions in programming languages, including
Also very shy, so I'm good. Thank you so much.
Thank you.
I'm so sorry.
Sorry.
Thank you so much. Je vois que tous les copains sont là. This talk is about a simple problem due to Yves Berthaud. I would like to thank Hak Choo-ho and Yule Sui for the invitation. And SAS is a big conference, it's a huge honor. I will try to make it worth your time. And the thanks recapitulate to all the successive organizers of SAS, all the way back to Patrick Couzeau and Radia Couzeau. So this talk is generally analytical rather than specifically about static program analysis. So thank you for bearing with that. So more foundational than about the assumption than the contribution. So the way it is structured is with a progressive series of exercises where a pattern can be identified and then abstracted, and then the end result coincides with something else. Okay, so it's a demo of the values of being analytical to make an exploration, and is born in the classroom. So overall, it's a fun exploratory lab session where the students can experience a computational and a mathematical adventure. And I have it from good authority, namely Christopher Strachey. In 1963, in a letter when he was working as a head master, I found in the Bodleian library something that he wrote, and I picked the quote, which is really great. And it is that we should encourage the young people who are now learning about computers to feel some of the spirit of intellectual adventure, which I think computing can engender. So going to live up to that. Christopher Strachey was a giant, obviously. We are lucky to have his last PhD student, Peter Mosses, this week is giving 2 talks, and he's standing on the shoulders of that giant. So no pressure on him, but you really should attend these 2 talks. So the challenge today is that our students are insecure and their knowledge is fragmented and kaleidoscopic. And so that's the bad news. The good news is that they have one survival skill. They understand what the teacher wants and they deliver exactly that. Okay? And that's the angle for the teacher. You want to connect with your students and elicit anything from them. You have that which is actionable. Funny story, when I joined the LNUS and I was giving my first lecture, there was a group of concerned students who came to see me at the break, and then they said that something I did not understand how things work here, okay, because what I'm supposed to do is to tell them what they want, what I want them to do, and then they will deliver exactly that. So, and it's not clear what I want, so they asked me, what do you want? Right? Pretty smart. So I told them, well, I would like you for the following lecture to be well prepared based on what you have learned in this lecture. I would like you to successfully apply for a summer internship and use the skills that you have applied. Then there was a long pause, and then they said, you still don't understand, Professor. It doesn't work like that. Okay? So the students today, they have that one survival skill, which is how they have survived. That's why they're here. If they are here, it's because they have passed all the exams, because they have learned what the teacher wants. And then if you, okay, fire and forget, right? So that's the challenge. So the enabler is the rock-proof assistant. And the thing is that if you ask a student what's a proof, they will tell you a proof is what the teacher says it is. Okay? And then when they have had several teachers, they say, so of course they're not the same teacher, not the same proofs. See, kaleidoscopic. But the revelation with a proof assistant is that proof has a syntax, like a programming language. And so you have a fighting chance. Okay, there's something objective in this sea of subjectivity in which they are trying to swim. And actually theorems have a syntax as well on the rest. So that means that the stuff that they have learned in computing is actually useful for mathematics, which gives them some element of stability, okay? And so you can make them grow into becoming secure in their knowledge, okay? That what I know is actionable, okay? So compare that, for example, with, okay, no name, but a research-based kind of teaching where every time there is a new exercise, you need to invent something new. And then the one who survived that diet passed the next class. This one is actually cultivating the insecurity of the students because it's demonstrating them week after week that what they learn is useless because they never reuse it. They ceaselessly need to invent new things. And that's a problem. Okay, all right. So ROG is an enabler, not a silver bullet. Here is a fun exercise that I give in like week 3. And by then, the students, they know that propositions are types and that proofs are programs. And they can talk about it. It's really beautiful, okay? And they're exactly repeating what I've said. So once the week 1 has been about functional programming, and before that we had studied OCaml, and one of the exercises they needed to do to make them, well, I make them write abstract syntax tree based on the grammar, and if the grammar is in logical form, they write something called a proof tree, which is isomorphic to abstract syntax tree. And again, they say whatever, and they learn that. So they have a skill already where I give them a polymorphic type, and then they come up with a term. And they draw the proof tree based on the syntax rule. And that's first-year students. So that means that the first programming exercise where I give them 14 types in need of a term, they know that stuff. And then in the second week, we have seen how to prove logical propositions. So I give them 14 propositions in need of a proof. And they can just apply what they have learned, okay? The fact 14 is a weird number, and the fact that it's twice the same number should alert them, but it doesn't, okay? Because when you work in group, dividing does not conquer. So half of the students in the group do the first, the other half do the other one, they concatenate, and again, another week well spent. And so they don't realize that the types of the proposition are the same, and they solve the exercise independently. Okay, which is the perfect example of the students regurgitating what the teacher has said without reflecting. So, so to make the horse drink, there's a famous saying that you can lead a horse to the water, but you cannot make it drink. However, you can first make it thirsty. That really helps, okay? Simple but effective. So this is the time to make them realize that, okay, yes, the syntax, the BNF of the type and the BNF of the propositions are isomorphic. We can convert one to the other, and the two conversion functions are inverse. So, okay, we can see that the types and the propositions are the same. But the programs don't look like the proof, okay? Well, some say lambda, okay, fun. The other one has intro, apply. So what? So, then to elicit the understanding, I asked them, well, how could we unparse the proof into something which is perhaps more relatable? And then there is a vast question mark that floats around the room and nobody gets it. So, tada, show proof. And then the unparsed proof is written as the program. And oh my gosh, that program is exactly the program that they wrote in their first series of exercise, and it really opens their eyes. And afterwards they say, wow, programs are proofs and proofs are program, but now they get it because it comes from inside. Okay, so shocker. It's really hard to elicit understanding from others. Anyway, here is Hilberto's simple problem. Consider two consecutive natural numbers. Is their product even? Okay, note it's written in English. So, so by then the students have been doing some proofs and they have never written theorem themselves. Think about that. All the theorems that they had to prove have been given to them, so they have no experience in writing theorems. So need to analyze the student, decompose it into components, and then formalize the components and recompose it into a statement, which is not easy at all because the variety of the statements is really huge. But once they have the theorem, then they can outline some proof strategy, what they are going to do. And I warn them that the choice of proof is going to be to reflect how they think primarily, like a programmer or like a mathematician or like. So now the adventure is becoming one of self-discovery. So I have their attention. And the proof strategy roughly are off the shelf. So indeed, the Coq library the ROC library has what you need to make the proof. So that's very easy. The spine is at work. The brain is very happily resting. It can be by induction. Okay, and most of the students start that and give up at the induction step. And or using a lemma. So you prove independently that a number is even or odd, and then the theorem is a corollary of that. And it can be operational, so they also have programmed even predicate, and they prove the soundness and completeness. So the two sides of the same coin, which they don't realize, but they are getting there. So after a while, they all have written proofs, and they all talk a lot about, I tried this, but then I should have trusted myself more. So there's a lot of activity. It's heartwarming. So let's generalize Eve's problem. Consider 3 consecutive natural numbers. Okay, so to me, it was obvious that the same proof technique should work for 3, right? The product should be divisible by 3. You reuse the same method as for 2. But for the students who have been raised in a diet of invent your way, they don't reuse what they have done. So they're nurturing their insecurity. So, but a bit of reflection makes them realize that, yes, their product should be divisible by 3, and the argument is, well, okay, either it's equal to 0, modulo 3, or 1, or 2, and then there are 3 cases instead of 2, and yeah, it works. But the product is also divisible by 2, because 3 consecutive numbers include 2 consecutive numbers, and we just saw that it was divisible by 2, so divisible by 6. And if we generalize them to 4 consecutive natural numbers, then the same reasoning applies, should be divisible by 4, by the same rule, and that's an easy one. But they're also divisible by 3, because the product of 4 consecutive numbers includes the product of 3 consecutive numbers, and by 2. So, by 24. Now, do the proof scale as they go, okay? And they realize that only the induction proof scales, all the other ones are just growing and growing and becoming unmanageable, but not the induction proof. Surprise. So here is a third generalization. Consider 5 consecutive numbers. So again, should be divisible by 5, but also by 4, and also by 3, and also by 2, so 120. And by then, these numbers, 2, 6, 24, and 120, they have seen them before, namely when they were writing unit tests for the factorial function. So, that's a property. And in fact, it's not just that, but the induction proof for 3 is using the theorem for 2 in the induction step. And the induction proof for 4 is using the theorem for 3 in the induction step. And the induction proof for 5 using the previous theorem for 4. And for that, you need to write all the proofs uniformly, which is not a trivial thing for undergraduate students. But they see that there is something that looks the same and that can be actually made the same. And then they realize that, well, their proof is the same, okay, has the same structure. So that suggests a generalization where we quantify the number of consecutive numbers. And then we prove this generalization by nested induction. And the base case, 2 consecutive numbers, that's Yves Berthaud's simple problem. And the induction step is using the induction hypothesis instead of invoking the previous theorem. And now this is a proof that comes from inside. It's a generalization of what they have done. On when the student invents something or something comes from inside, they remember it forever. You know, Confucius. I hear and I forget, I see and I forget, I do and I remember. And then it's further to generalize to 1 consecutive natural number and 0 consecutive natural number. Okay, that's simple. So now we have the product of m consecutive numbers, n plus 1 plus da 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 plus n plus m minus 1 is divisible by factorial of m. And okay, déjà vu all over again. In the first published proof of Fermat's little theorem, Euler comes up with exactly that fraction and points out that despite its specification as a fraction, it gives an integer. That's what it means to be divisible. So we can also make a simple variant where when we have consecutive numbers like that, if n is big enough, then we can also say, well, n is big enough, and then we multiply it with the m predecessors. So the question is, since for any m on n where m is greater than m, the product of the m consecutive numbers is divisible by m, factorial of m, what is the result of this division? And by the way, did you know about, have you met that guy before? Déjà vu, okay. So you stare at n times n minus 1 times dot 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 times n minus m plus 1, you divide that by factorial of m, and déjà vu, okay? And the answer is, for some students, is aha! And for others, it's oh my goodness. And then the funny thing is that they start to talk, but it means that, okay? And then their hands move in a very characteristic way when they connect things. And that's not the first time that it happens in the lab session, so that's fun. Okay, see, no spoiler. So the benefits of the lab session, aside one, is Bloom's taxonomy of learning. So Bloom's taxonomy of learning, I learned about that to write evaluation letters of peer reviews for my colleagues. It's fun. You can check it in the Wikipedia page, and if you have to write a recommendation letter and talk about the teaching part, you can use professionally Bloom's taxonomy letter, and that will impress the babes. All right, so it basically covers all the aspects of learning, and it culminates with reflecting. And it's reflecting in spades here. Okay, so that's kind of the independent assessment. The benefits of the lab session is that figuring things out is a joy, okay? Richard Feynman wrote a book with that title. And the reason is that it does make one feel smarter, and that's my secret weapon for the undergrad student to make them study computer science. When you start to feel smarter, it's extremely addictive. So now I have them. And it's enough to feed them with exercise that make them feel smarter every time, and that sharpens their mind, and it works beautifully. Okay. Now the reason why ROC works wonderfully, okay, I'm sorry, not SS Reflect, and definitely not Crush and Simple and whatever, okay, is that its language of tactic, and it struck me one day. It seems completely inspired by the Bourbaki way of writing proofs. It's very French, okay? But when all the people who have made the Coq proof at ROC, okay, at the time Coq, they were raised in that culture. So there's something completely natural when you write intro and when you write apply, and when you, it's almost like you read a well-structured proof by hand, and to me, it makes a wonderful connection with the people who have independently have touched mathematics with this kind of structured proof. So it's very subliminal, it's unstated, but that's, I believe, one of the reasons why the Coq proof assistant has such an impact. Again, if it's not done with Crush and the things that make your eye go blur and you can't see what the proof is doing. So once they're in control, then it's reproducible, it's extensible, and a lot of fun is being had by all. All right, so if you look at the tree of knowledge of the students, at the beginning it's a completely disconnected graph, and then it's slowly growing into a DAG where they are connected components, and the students start to get the reflex that learning is not learning something new, and then something new, and then something new, and then something new ad libitum. Yep. So I would just like to add a word about LLMs. So until not long ago, when I was asking these questions to an LLM, the answers were obviously self-assured. They were voluble, okay, talks a lot, and they are grossly unsound and grossly incomplete. So there's a perfect thing to show the students to make them mindful that it's not really obvious. You should be careful with your trust. Now, LLMs are a huge vacuum cleaner nowadays. And so now, okay, if the students ask the same questions, then they get the answers that are self-assured, that are voluble, and that mention the solution presented here as an evidence. Okay, which, so LLMs are turning into a major spoiler, and that's a problem for teaching. It's already a problem for teachers who think that teaching is a solved problem, because now you just need to mechanize that and then automate it and then delegate it to AIs. Okay, done. Kind of, well, creating their own or raising their own tombstone, because once the AI is there, we don't need the teachers anymore. But the fun thing about students, and I've been interacting with them for a long while now, is that the way they don't understand seems completely unbound. Every year I meet a student who doesn't understand something in a new way. And of course that means that I pay attention to what the students do. So, and the students they're in complete shock, okay? I get amazing comments like, I've learned many programming languages now, I'll never learn it based on the grammar. Okay, so the most important thing linguistically about programming language compared with natural language, okay, it's not the linguists that are kind of running after the language trying to describe a best approximation of and then upgrading it every now and then. Well, in programming language, not so. The grammar is not describing the language, it is prescribing the language. And if it is not syntactically correct, it is not correct. And therefore, if you understand the grammar, you understand the error messages. So delegating and saying, well, the error message of the compiler are self-explanatory, it's an intellectual failure. And it doesn't generate students who are dependable, and they are very insecure, for sure. Okay, so the fact that that programming language have a grammar which prescribes what a program should be is really cool that Coq is doing the same, Rock. And there is a grammar. Proofs have a logic. Okay, I mean, I'm talking informally here, not just intuitionistic logic. And that has all the elements to build a area of knowledge in which the students grow secure. And then they can become creative. Okay, so this was the first thing. The students saying, I learned many programming languages. The first time I'm being taught in a grammatical way where you go from syntax construct to syntax construct, and then you're snowballing and growing the language on us. And it works so much better. Well, yeah. And the other thing is, well, nobody has ever read my programs. Boo, hoo. So we have students now that nobody has read their program and read their report. They don't write report anyway. So it's really fun to meet students who just arrive like at the School of Computing, which is an elite school, and they talk with authority about research. I met one at the last session, and he beeline on me, had a question: how do I publish my research? You're in high school, right? Yeah. But I've used an LLM, so I want to publish my research. Okay, let's talk about what you mean by research, okay? So I tried, okay, beautiful word in French, comparison is not reason. It rhymes beautifully, much better in French, but it rhymes in English well enough. So I asked him, okay, fine, yeah, okay, I take you as you are, fine, but suppose that you were studying mathematics. Do you think that you could arrive on a lot of research? Oh, no, of course not. Okay, suppose that you study physics. Okay, any hard science? No, I couldn't. Okay, suppose that you want to study surgery. Do you think that after 6 months of learning Python, you could make major surgery? You say, oh, of course not. Dentistry? No. Okay, so let's talk about martial arts. Okay, let's talk about dancing. Let's talk about cooking. Okay, like the sushi master was so impressive. I mean, he has his 10 fingers, even though he's using daily a knife which is extremely sharp. So he learned that, okay? He learned the moves and then he accelerated. And we don't have that at all when we teach computing, like at all. It's completely ludicrous. LLMs are going to make it worse. And this is just a warning that I wanted to state. So you need a teacher who talks to the students, okay, who exercise empathy, who identify the errors on why he or she is making the error, okay. At TLNUS, we had like 50% of female students and 0% of problem to make CS, computer science, well, for all, not just for some. And it was just based on being systematic and being logical and using grammars and giving feedback and so on. And it also worked at SOC, so the students are liking that. And yes, they have to work more. But on the other hand, they kind of they pass a threshold when they realize, wow, when I'm writing my report, it forces me to articulate what I'm doing. And then it actually, I understand better. I make progress by describing what I'm doing. Okay, and we have a writer center where it's the holy grail, okay? And the fact that we can do it in computer science stuns them. Another example is, so writing their reports. Another example, which is fun, is that if you're empathetic, then every semester that I was teaching, I always met a student who had an epiphany. You know what is an epiphany? You see God, okay? And the student just says, everything makes sense. It's completely amazing. And now all my courses are easy, and they really literally levitate, okay? And then managing a student who has an epiphany that is not easy, okay? You need to be intensely respectful, and of course he sees you as their guru, which is not a good thing. So you need to put their feedback on earth, and then. But it's fun to teach, okay? And the students they feel very rewarded about that. Okay. So as parting words, before I can take questions, I hope that this talk has illustrated the foundational value of SAS, which is the value of being analytical, and that can be individually, okay, the person who thinks in a reflective way. It can be dynamically, it can be statically, okay? You want to do dynamic analysis, you want to do a static analysis, you want to do it mechanically, or you want to do it automatically. But all of that is based on being analytical, which is the foundational value of SAS, I would believe. Thank you very much. I'm more than happy to take questions. If there are no questions, I can tell you a couple more stories.
Tell us a story.
Here is a story. So to teach in Asia is a challenge, okay? because the Asian students, they are not like the European students, they are not like the Northern American students. And one of the reasons is language. So if you look at the sense of humor in Asia, it's much more situational than linguistic. And the way I teach computer science is extremely linguistic. So it's not just a blurb, it's a structured blurb, okay? As a grammar, a syntax, a semantics, logic. And to make the students appreciate that is not easy. So here is two things that I did, which worked. So that was the first semester I was teaching at ELN-US, and they gave me a course to teach in the morning, which they never did again. And so the students were just barely awake. I suddenly was barely awake. And I was teaching them algorithms and data structures. And so one day, when there was a general brouhaha at the beginning of the class, I stepped into the brouhaha, and then I said, guys! Okay, yeah, it's supposed to make noise. What's the favorite beat of computer scientists? So now they look at me, what? Honestly, what does it have to do with computer science and liberal arts, okay? What is this question? So they have no idea. So they express that, and then I look completely catastrophed. And I tell them, well, it's an algorithm, okay? And half of the students burst into laughter, and the other half say, what? And they were the Asians who are not clued in on the linguistic aspect. So a few weeks later, okay, same, early morning, not really awake, the students are barely awake, and they are big brouhaha. So I jump into the brouhaha, and then I say, guys, what's the favorite beat of mathematicians? And then something very funny happened. There was one student who just jumped out, and his brain just worked very fast. And then he said, ha! This is a question that he has already asked. I know the answer, and so I'm going to repeat it. And he's going to be happy, because the point of learning is that you repeat what the teacher says. So very quickly he says, an algorithm! And now he's expect congratulations. And the fun thing is that half of the class said, no! He didn't say computer scientist, he said mathematician. And that was so nice to see that there were half of the students who got it. They realized that words mean something. And so they talk to each other, and they don't get it. And so they look at me and go, oh, guys, a logarithm! Yeah, it's lame, but it works, okay? So I'll tell you how to teach polymorphism to your undergraduate students. And you do that with a dad joke, all right? That works amazingly. Okay, so polymorphism, there's no simple definition of polymorphism. The nicest one, of course, is in Galena. It's a parameterized lambda whose parameter is a type. So. But except for that, so little Johnny is coming back from school, and he talks to his dad. And his dad says, so little Johnny, Toto in French, how is it going at school? And little Johnny said, well, not very well. Okay, what's up? I have problems with additions. But the dad says, like Matthew, I will help you. My son, I'm going to help you. Okay, so look. Here are 2 apples, okay? 2 apples, right? And then I give you a 3rd apple. Okay. How many apples do you have? And the dad feels really good, okay? And then little Johnny burst into tears. And then he says, I don't know, because we count in oranges at school. Okay? And there is an electric discharge in the room, and they understand polymorphism. Okay? And so the unit, it becomes the, yeah. All right? Obviously I can go on, but you sure you don't have any questions? Thank you.
I'm reluctant because your stories are better than my question, but It sounds like your students are extremely fortunate. I think so. Have you thought about how to get more teachers, especially teachers who are not here, would not be here, let's say, to teach this way? Is this something we can do?
I wrote lecture notes, but it's complicated. So that's the mark of the success of okay, I'm sorry. The question was, is it reproducible by others? Okay. So at Yale and US, that was not a question because there was nobody else who wanted to mix liberal arts and computer science together. So I needed to invent everything from scratch. And then the standard reaction. So one of the things that works amazingly well. Okay, so you teach. Okay. So how many times in the classroom have you heard the voice of all the students in the classroom? Okay, and the answer is never.
It's hard.
But never.
Yeah.
Not all of them. So the trick, which I implemented, is to write a theater play about the process of figuring things out. It requires a lot of empathy. And then the students have access to the theater play and you make them read it, one after the other. And then they read with the tone and they use the words and that's really, really critical. I remember teaching in Denmark and I was teaching scheme, all right? And at the end of the semester, there were still students who had not connected the word scheme and the way it was written. So they were saying, scum? So, and that's because they did not speak. So writing theater plays about not what you want to tell them, because you can always tell, but how they should figure it out. So the problem with teaching is nobody tells you how to learn and how to understand. So writing theater plays where the students enact their learning and talk, and there is one, and it's not character based. There is no character evolution. It's not like literature. That activates all the students. And I thought that that's something that would be reproducible easily, but then I'm told that it is not. So, yeah.
Yeah.
So I'm sorry, I don't have any good answer to your good question.
Yeah, we don't. Thank you.
Thank you too.
I think for most teachers, what we want is students to have epiphanies. What we assess is their written work, their programs, their essays, whatever, and that has been a poor proxy for detecting when epiphanies have occurred. As you point out, with large language models, that whole process of assessing written outputs is defunct now. It doesn't work. So do you have any thoughts about how to assess which students have had the epiphany or not?
So how do you assess whether a student has had an epiphany or not? Well, usually the fact that they levitate is a pretty good indicator. The fact that everything is easy to them and they speak and they typically come to your office. But that's only one per semester, so it's very much an outlier. But it's there, so you cannot ignore it. But it's kind of hard because nobody has read. But I mean, it's the same for mathematicians. I remember talking to Peter Axel at the INRIA week where there was Wojciechowski and all the big shots. Okay, so that was a whole week in Sophia Antipolis. 10 years ago or more. And I went to talk to each of the mathematicians that I could, and this is all of them, and I asked them, do you read the proof of the other people when you review their papers? And each of them said, of course not. Okay, why? And what do you do? Okay, and Peter Axel told me, well, I mean, I look at the statement of the theorem, I vaguely look at it, and I try to figure it out, and if I'm convinced, okay, good enough. So that explains at the end of that meeting why Vladimir Vodevosky accepted his love for the Coq-proof assistant, because there was someone who checked his proofs, which nobody does. So that's a real problem in mathematics, and there's a problem everywhere else. How do you want to improve your writing? Well, it requires others. So how do you automate that? And another story about Wojciechowski. So Magritte, this is not a pipe, okay? That's kind of the background of the story. A pointer is not what is being pointed at, and so on. So at the end of the meeting, Wojciechowski gives this talk, and it was hilarious, absolutely hilarious. He was giving the first talk of every computer scientist who has never given a talk. So he said, blah, blah, let me show you my code. And then he showed us his code and his code, and he was talking about his code, and he felt great. Nobody understood a word, obviously, because it's his code, right? So there was no like, here is the structure of the code and the way it works. No, look, it's... Anyway, at the end of his talk, everybody important speaks, and at one point, well, there are so many important things to say, so there is a silence. And so I grabbed the microphone, and then I asked him, well, how does he feel about writing his proof, and that his proof is being checked? And then he said, oh, it's so great, it's such a relief, and so on. And then I saw something extremely unusual. Yves Berthaud, the guy there, flat out running across the field. He was running, and he grabbed the microphone, and then he said, but these proofs are not proofs, they are representation of proof. And that's so great. Okay, so there is a compound bunch of problems, and I'm really sorry there was a question, but I was talking too long. Thank you.
I didn't want to take away another story. Do you have more stories?
I'm sorry?
Okay, just a quick one. I think you may have covered this already. Sorry if I missed it. What does it mean to be analytical?
Oh, yeah, that's a good one. So whenever we are being asked a question in a talk on something, it's either about your contribution or about your assumptions, and it's super important to distinguish them. And this is a question about assumption. Okay, so yeah, I did not define that. On the ground, that is called static analysis symposium. So I was taking the safe assumption that people already understand the A in SAS. But I can explain what symposium means, okay? Originally, that means, it means the place where you congregate to drink, okay? So analytical, oh gosh. It would be, can we talk about that afterwards?
I'll settle for symposium, so thank you very much.
Sure. All right. Thank you so much.
Okay, let's get started. Our second keynote speaker is Ilya Sergey from National University of Singapore. And Ilya has done so many works on semantics and languages, smart contract languages. And for today, today's talk title is Multimodal Verification of Distributed Systems in Lean. So please join me in welcoming him.
Thank you so much, Hector, for the introduction and for the invitation. I realize that I'm competing for your attention with the session of distinguished ICFP papers, so even more delighted that you have come here. So I hope I hope to make it worth your while. I'm going to talk about the work that I'm very excited about. This is something that has happened over the last year and a half. And as always, the main credit goes to my PhD students, Georgia Perle, Vova Gladstein, and Chuan Zhao, and also Elad Kinsbrunner, who did an internship with us. So the theme of reasoning about distributed protocols and distributed systems has been a long-running topic in my group, and this work is about consolidating many ideas and many lines of thinking in what we hope is going to be a significant advance in making verified distributed systems a reality. So the title has the word multimodal in it, which might be unfamiliar to some of you, so let me unpack that. So in fact, what I'm going to present is a framework that allows you to reason about distributed protocols in a way that combines both automatic reasoning techniques with interactive proofs. And for all of that, we are going to use Lean as a lingua franca, as main encompassing framework. So let's start from the basics. Distributed protocols are algorithms that define how multiple parties, typically called agents or nodes, collaborate together to achieve some common goal. And this is a problem which is almost as old as computing, and many of us know the classical papers such as the times clocks and the ordering of events by Leslie Lamport, the algorithms for mutual exclusion such as Ricard-Agarwala or Suzuki-Kazami constructions, or constructions which are very prominently used in distributed systems even today, such as the two-phase commit. So I couldn't find a canonical reference, so here is the slide from Leslie Lamport's video class on TLA+, which is a fantastic teaching material, by the way. Consider checking it out. So he explains two-phase commit in terms of marriages. So the story doesn't end here, and distributed protocols, they become really interesting when you realize that their main purpose is to connect the parties across multiple physical locations. And when we have these geo-distributed systems, some nodes, some parties might go dark, might stop responding, the messages might be lost, and we can experience all kinds of failures. This is when the problem of specifying and reasoning about distributed systems becomes interesting, and this is the problem to which we owe some of the most prominent constructions, such as the view-stamped replication, Paxos consensus protocols for reaching the agreement between multi-parties, and many other things. So some of these works are more modern, some of them are by my colleagues, but this is still a very much active area to develop protocols for reaching an agreement in the presence of failures. But the story doesn't end even there, because not only parties might fail, they might intentionally misbehave to make the protocol, to make it difficult for the honest participants to achieve the agreement. And you can think of systems such as blockchain protocols, where people have like very real financial incentives to behave maliciously. So they can, for example, double spend the digital currency. This is a very popular problem, as many things in distributed computing. The name has been coined by Leslie Lamport as the Byzantine general problems, when multiple generals in the Byzantine army try to agree with each other by sending messengers, whether they attack next morning or whether they retreat, and some of these generals might be traitors. So this is the analogy that goes a long way, and this is what has been used as a main premise to build protocols for what's called Byzantine fault tolerance, with the probably one of the most famous one being the PBFT by Miguel Castro and Barbara Liskov. Yeah, that Liskov of substitution principle, that's the same person. So, and there are other more popular construction nowadays, such as hot stuff and protocols for stellar consensus and others and others and others. And actually, this is a very active area, and at least 5 or 6 papers on the BFT protocols are published at every major security conference, such as Oakland or CCS or Usenix every year. So people work on this stuff quite actively, and obviously, they're very much interested in getting these protocols right. Not just their implementation, but the algorithmic design of these systems. And bugs in these protocols, they happen surprisingly frequent, and they are published in the papers, and they sort of poison the implementation. So George, who is one of the main drivers of this work, even keeps this list on GitHub for bugs in distributed protocols that keeps being updated with people submitting PRs with more stuff being discovered. So what kind of manifests the bug? So a bug is a violation of one of the desired properties. And those properties that we want to enforce fall into 2 classes. As we know, we have safety properties, meaning that bad things will not happen during the lifetime of our system as the protocol executes. And there are also liveness properties, something that we frequently specify in logics like LTL, that say that good things will eventually happen. Practitioners like to focus on safety properties more because these are the properties that can be somewhat reliably discovered with the conventional black box testing with finite counterexamples. So if the bug happens, you have a chance to run the system until it happens. If your bug means that certain events will never happen, this is much more difficult to discover unless you do a very deep intrinsic analysis of the workings of your system and try to detect something like cycles in its logic. Okay, so let's focus on how can we verify the properties of distributed protocol, safety or liveness. And indeed, this is the problem that has received quite a bit of attention in the static analysis and formal methods communities, and some solutions to specify and formally verify safety properties of formal protocols date back at least 20 years. I'm quite sure that this is not the first paper, but this is the one which is relatively well known by Maro Jaskelev and Stefan Mertz, who proved the correctness of a version of Paxos in Isabel Hope prover. And the works were coming from their own, so some of them are more prominent, some of them were focusing not just the protocols, but the systems. Some of them, such as Ivy, delivered frameworks which are supposed to be used by the protocol designers, and these works keep coming. So as you can see, like some of them, okay, I even very graciously mentioned some work from my lab, but the point is that how many of you have heard of protocols such as Lido or Bifos or Aneris or Velizarius? Okay, so this is obviously a very biased audience. None of the practitioners I've spoken to ever heard of any of those. What have they heard of? TLA Plus. So TLA Plus is the tool which has been conceived and designed by Lamport and then developed by folks at Microsoft, and it has an amazingly effective model checker, which doesn't attempt to do any verification in a symbolic sense. It takes the model of a distributed protocol and it just runs it up to a certain depth of the execution, which turns out to be a very effective way to discover bugs in the designs. Sure, the bugs occasionally get missed. For example, one of the known cases is how the Raft consensus protocol had bug in its definition, which hasn't been caught by running the TLA plus model, but still, this tool has a relatively low entrance threshold, and it has a very nice feedback loop. So it actually makes it quite pleasant to prototype distributed protocols, and hence industry uses it. So, but this is not something that you can use to verify that your system, well, is devoid of any violations of your desired safety or liveness property. It's a tool for bug finding. So how can we bridge the gap? So to do that, and also to make a practical tool, we need to understand what makes TLA plus so successful. So what it makes successful is that, well, the formalization effort, which is, well, effectively the probability that your tool has, that your system has no bugs, kind of, with TLA plus, it's like relatively low, but the formalization effort is also low, and if you go with formal verification, you get to this angle. But people in industry, they're really not interested in the probability of having no bugs. they are interested in a very ephemeral notion of the percentage of bugs that you have found. And this is where, somewhat informally, TLA plus scores really, really high. Because if with very small formalization effort, you already manage to eviscerate 99.9% of bugs, and well, who cares that something might be lingering? It might still be critical, so you still care about that. But it's typically good enough for most of the practical purposes. So how can we get there? And how can we avoid this really, really steep curve of the formalization effort that is required out of the foundational tools to get to the same percentage of bugs? Because as we all know, if you try to write your system in your favorite proof assistant, even if you're really, really good at quick prototyping, you will probably spend quite a while until you get your first QED for the interesting property. So you will spend a lot of time proving invariance and auxiliary lemmas. So TLA plus is so successful because it has this feedback loop between the engineer and the tool, where the protocol, where the engineer gives a definition of the protocol and the properties with no tools whatsoever, because remember, it's just for testing, and TLA plus gives back the check mark saying, okay, up to certain depths, I found no bugs, or it gives you counterexamples. And those counterexamples, they are very graphical, so they are as good as you can get for in terms of debugging. How can we get there? And how can we also make it so from this model, we can also gradually go to verifying distributed protocols? And well, this is where we started. So we actually really wanted to get into this gray area where TLA plus doesn't do so well, which has to do with Byzantine failures. So what makes Byzantine failures, the adversaries, difficult to model is that you need to be as smart as the adversary. You really need to be able to predict every move of the adversarial player to model it precisely. Whereas if you think in terms of symbolic reasoning, it's actually much easier. You just say what the adversary cannot do for sure. For example, it cannot reverse hash functions, or it cannot forge signatures. And then anything else it can do, and this is something that you can reason symbolically. Well, so there is a small family of tools based on first-order logic, most prominently Ivy and its version MyPy, that actually get in this gray area, and they get somewhat better experience in terms of this feedback loop, because these are the tools that are based on decidable fragments of first-order logic, meaning that most of the proofs can be constructed automatically with the help of tools such as SMT solvers. The price to pay is that certain properties we just cannot express easily, because these tools, they work in a somewhat limited logic compared to tools such as Rock, Agda, or Lean, but they get an automation. So we really want to get somewhere here. We can get all the good things, but we can also state properties that are undecidable by the nature, and if there is a property for which we want to write an interactive proof because SMT is not powerful enough, we should have this mode. So this is a relatively narrow space, but this is what made this problem very interesting for us as researchers, and with the hope that we could also deliver a useful tool. So we want to be here. So let's try to analyze what the world has now and how can we contribute. So TLA plus is amazingly expressive, so you can write pretty much arbitrary properties and get fast feedback. If you want to prove properties, whether it's complex properties and higher order logic, or something that requires first order logic and proof automation using SMT, in principle you can do that. So not many people know, but TLA comes with the proof system, which few people use, and it even comes with some support with SMT solvers. It's just not something that it's optimized for, and the experience is somewhat subpar. So many people still use TLA plus as a glorified testing tool. However, if we look at the research that typically gets published at conferences like UPSLA, POPO, PODI, or even SOSP, this is where people really focus on interesting properties that require full-blown higher-order logic. And sadly, this is where you have close to no automation, and you have no fast feedback, because these are all the efforts that carried out by big labs, usually in the course of multiple person years, well, culminating with the paper, but no one in industry giving a damn about it. So something which does slightly better are the industrial efforts such as Ironfleet, which pursues the same goal but adopts a tool based on the automated prover, which was Daphne. So at least some automation has been done there, and this was actually a pretty good experiment. Ivy in MyPy suggests a different trade-off when you sacrifice the expressivity of the property, and you also cannot do much about the interactive proofs, although there are some attempts to extend them, but you get the fast feedback because your SMT solver either gives you the desired ansat, meaning that your specification holds, or it gives you a counterexample, and you get the automation thanks to that. Okay, how about we can How can we get all these things together? And this is what was the goal of this experiment, which resulted in a tool called Whale, which I'm going to present. So Whale actually achieves all these 4 properties, and it's still very much a work in progress in the sense that we are trying to make the user experience even better. But let me just tell you that the arbitrary properties is something that you can specify in Whale, because Whale is just a library or a domain-specific language on top of the calculus of construction as implemented by the Lean proof assistant. Furthermore, it's a shallowly embedded library, meaning that the programming language in which you define your models in Whale is very much the language of Lean itself, with some extensions for the quality of life if you want to have easier time discharging your proof applications. How do we achieve fast feedback? Well, we go full in with symbolic model checking, where we generate our queries, well, basically our verification conditions are the queries that are dispatched with the help of an SMT solver. So they are proven or disproven. And in the more modern version of Whale, which I'm not going to show, we can even run the concrete state model checking the same way as TLA Plus does. But the nice thing is that by means of being just a library on top of Lean Proof Assistant, we can also have interactive proofs for the properties that are not easily dischargeable with an SMT solver. And as mentioned, by using an array of tools that interface between the higher order logic of Lean and the first order logic that SMT solvers take in the form of SMT lib queries, we can also prove many obligations as just push the button without writing any proof script in Whale using SMT solvers. Okay, so that was the premise of what we wanted to get and what ostensibly we have achieved. And I'm going to spend the rest of my talk trying to convince you that we are either there or at least on the right path, and see if you have some feedback which we would like to incorporate. So to show you the tool in action, let's go with the hello world of verified distributed protocols. Really the simplest application that usually comes to mind when someone wants to specify a distributed protocol, which is a leader election in a ring topology. So the idea is very simple. We have the finite known number of nodes with identities, and the nodes themselves, they only know the identities of them, like of their own, but not of the other participants. But the identities, let's say natural numbers, they are totally ordered. Not necessarily contiguously, there might be gaps and whatnot. So the goal is for this bunch of nodes to select someone that they perceive as a leader, and for the node that is selected as a leader to know that it is a leader. So how that is achieved? The protocol is actually very simple. So each node sends its own, and each node also knows the topology in the sense that it knows who is its next neighbor. So you can think of it ordered clockwise or counterclockwise. This is actually not that important. So each node only knows its next neighbor. So each node sends the message with its own identity to its next neighbor. For example, the node with identity 1 sends its identifier to 5. And so do all other nodes. And each node, upon receiving the message, if it has received with the node with the larger identifier, it then passes it through and sends it to its next neighbor. Otherwise, it just consumes this message and mutes it. So for example, the message from 1 to 5 doesn't go any further because 1 is smaller than 5. But the message from 3 to 1 goes further, so by 1 relaying it to 5 because 3 is larger than 1. And as you can imagine, what's going to happen is that after the protocol kind of comes to the stable state, there's going to be only one message that, well, logically made the full round. And this is the message from the node with the larger identifier to itself. In this case, the message from 5 to 5. So the node with this identifier, upon receiving the message from itself, knows that it has made the full round, which means that it is indeed the largest identifier in the ring, so it can proclaim itself to be the leader and start acting as such. And this protocol doesn't assume any sort of faults. Again, it's a hello world example, so we don't assume that the nodes, for example, lie about their identity. So, and when someone starts acting like a leader, all the nodes will supposedly take that this is the case. However, this protocol is subject to one non-trivial property. How do we know that there is exactly one leader? Well, humans are really good at mentally executing state transition systems. So running it on a bunch of finite examples in your head, you will see that it's highly unlikely that there will be two leaders, because effectively only the largest message will make the full round. But this is non-trivial reasoning. And the fact that there will be at most one leader at the protocol is a safety property that we want to hold over this system. So how can we specify and how can we verify that? Okay, so effectively, once the leader is elected, we want to make sure that there is at most one leader, or at any point of time there is at most one leader, because if like no leader is elected, then well, there is no leader. Okay, and this is something that I'm going to use as a running example to show how well works from the perspective of its user. So now I'm switching to, well, VS Code, well, in this case Cursor, but I'm not going to use any fancy AI to assist myself, and I'm going to show what the encoding of this protocol and what the verification looks like in Lean. So what you're looking at is, in fact, Lean, except, well, there are many keywords that are not really Lean keywords, well, because vanilla Lean like looks more or less like your favorite programming language. So this is what vanilla Lean looks like, with some theorem, which in this case is proven using SS reflex, so you don't have to know that, but this is a functional language. What I'm going to show you, it doesn't look like a functional language because, and this is the one main reason why we have decided to go with Lean, of an amazing power of Lean's metaprogramming. So effectively, through clever manipulation with the syntax and staging your passes, you can make Lean, you can disguise Lean to look like pretty much any language of your liking. So here, the story starts by us importing Veil as a library and opening the module in which we are going to define a distributed protocol or just a state transition system in Veil. So for that, we actually need surprisingly few components. And since we are interested in symbolic reasoning rather than concrete runnable implementation, which is something that I will leave aside in this talk, we actually don't need to provide that many details. For example, we don't need to say what is the exact type of the nodes. That might be integers, they might be strings, they might be reals, but importantly that this is some abstract type whose elements are totally ordered. So, and people who do proofs using SMT solvers, they can recognize of that as just us adding a theory of total orders into our context. So the tool could probably make use of that when it tries to construct the proof. Since this is a part of ICFP Splash, so talking to the ICFP crowd, how would you implement this theory? Well, the good news is that this is just a type class in Lean. So you can think of it that this whole verification is happening in the presence of an instance of this type class, but the instance is not required unless you will try to run it. You can just assume that you are implementing something that comes with this dictionary of facts and the dictionary of relations. So in addition, we want to describe that our nodes, they are ordered in the ring topology, for which, for historical reasons, we have this between type class. And I'm not going to go too deep into explaining this relation and for axioms for it, but you should believe me that basically that means that any two elements are in the ring topology and they are reachable from one another. Okay, so armed with these two theories on our nodes, we can now define our state of the protocol and the semantics of our protocol in the form of what can happen. The state is also quite simple. So we could define it as a data structures, but again, since we are going to use SMT a lot, a better choice is to define the components of our state as relations. You can read it as functions from node to bool, or in this case, node to prop. Like difference between bool and prop in this case is actually not that significant because we are reasoning about types with decidable equalities, and everything here is going to be decidable. In any event, so leader is something that says who is the leader, and this is something that assigns true or false to a node. And pending is the set of messages in flight. So instead of saying that this is a set, we just say that between the node, the source node and the target node, that there is a message. So this is a from and this is a to. And this is something that we model as a relation. So this is the state of our protocol. And in fact, again, this is not something that you have in the vanilla Lean. This is just a macro that generates Lean structure that has these two fields as relation and a constructor to make its instance. So what we are going to define next is an operational semantics of this protocol that says how it starts and how it evolves. So how it starts is, well, by saying that no one is a leader. So this is the certain syntactic convention that we took from the tool called Ivy, because lots of our examples came from it, and we thought it would make things easy to port, and people are sort of okay. So syntactic convention is when we write an undefined capitalized name. That means that's a variable which is universally quantified before the statement. So this sort of saying, like, for any n within our node type, make it not a leader. So make this the value of this relation false. And similarly, there are no messages in flight between any two nodes. So hopefully that is reasonable. This is not the only way you can define it, but this is the one encoding with which SMT solvers work quite well, and which is a fact that is known in the CAF community. So now going to the operational semantics of our protocol, we can say when it's okay for node n to send a message to the next node. So it turns out that it's okay only to send when the next is the immediate next node in the ring topology. So this is some kind of a mouthful, but in fact it means that there are no other nodes between n and next. And this is something that we also able to abbreviate later, because this is actually a very useful definition into what we call a ghost relation between the node and the next node. So meaning that, well, next is really a next. And then this is how we send the message. We just say that, well, now there is a message between n and next. So far, so good. Those of you who have seen some TLA+, this is actually not very different. So in TLA+, everything is a record or an array, and you basically set the entries of certain arrays to particular values. So this is about sending. So when a node receives a message with the ID of the sender ID in it, certain things might happen. So we know that in this case, this message should be present, the message from some ID to the node n. And here, just for the fun of it, we might either decide to keep this message, and this is a funny feature that allows you to model things such as non-deterministic duplication of messages. This just basically says, make this either true or false non-deterministically. The protocol will work either way. We can make it more strict, but this is just to showcase that as a specification language, well, also allows for non-determinism. Something that, well, it's kind of has a finicky semantics if you try to think in terms of pure functional programming. The interesting part happens here. So the node n, if it happens to be the ID of the sender, then we know that we are the leader, so this leadership relation becomes true for the node n. Alternatively, if the node itself is smaller or equal, well, in this case, strictly smaller than the ID, we relay this message to whoever is our next. Other than that, the message is either consumed in case this has been set to false, or just we leave things as they are, so the message can be received once again. So the protocol is idempotent in this sense. But again, this is the property that we can verify and something that we don't have to believe. So this effectively is how you write your protocol specifications in Vel. And the nice thing, this is just one way, and what you're looking here is the mix of vanilla Lean and our macro embedding of the verification language into Lean. For example, if then else is not a syntax that we had to encode as AST and mask. So this is actually Lean's vanilla if then else. And this assignment is something that we had to model, but the sequencing of this and this is actually something that, and since this ICFP I can say it openly, this is a monadic bind that changes the underlying state, symbolic or concrete accordingly, and this is where like all the magic of Lean comes in how it generates the theorems that we are about to prove. Okay, but so far, let's just think that, let's just agree that we have an informal understanding of this semantics. And actually, these transitions, they have multiple semantics, and we will see why that matters. And focus on the properties that we want to prove. So here's the property is the safety. So this is exactly what we had in the slide, saying that for any L1 and L2, if they are both leaders, then L1 is the same that L2. Quite a few things are commented because they are not necessarily to validate those properties, but since we want to have this quick feedback loop between the protocol designer and well, in the verification tool, let's try to make sure that our protocol is actually not flawed. So this property does indeed hold. And turns out that for that, we can go for a much cheaper solution than to verify that this property is not violated at any moment of time. Instead, we can say, well, this property is not violated after taking any 5 actions in this protocol, assuming that there are only 3 nodes in our protocol. So like we are making artificially a very small set of nodes, and we perform what's called symbolic model checking. So the reason why this is weaker than the verification that you typically want to have is that, well, we didn't model it for any arbitrary number of nodes, and we didn't model it for any arbitrary number of transitions. We had to finitize both. What makes it symbolic is that in fact we did not have to say which transitions we are going to take. So the tool has tried all of them. Where's the magic comes from? Oh, and at the end, we need to make sure that the property holds. And if you are puzzled, why do I have a negation here? Well, that's just because of De Morgan's law, right? And how the SMT solvers work. So the SMT solvers, they are very good to prove existential quantifiers, that there exists x such that phi of x. But if we want to prove that for all x, phi holds, we need to negate 5 and hope that SMT solvers will find no witnesses to that. So there is no x for which not phi of x holds. So that's why we negate the leader, and we really hope that SMT solver says that this is unsatisfiable situation. So this is unsatisfiable formula. But what exactly is the theorem that we are trying to prove? And this is kind of the big reveal. What you are going to see is just a lean theorem that the tool generates from you from the definition of the system that we have done before and this property. And the theorem effectively is like this. So it just says that, well, let's try to find intermediate states from 0 to 5 such that we can transition between each pair of them, and at the state of 5, this negated property should hold. So what we actually want to show that this theorem is not true. This is actually, this is how we're proving it. And the nice thing is that this is kind of property for which SMT solvers are really good for proving that it is either violated, so like it's not for all and there are some counterexamples, or it holds universally. For that, we have a tactic, which is actually just sending this statement of this theorem to an SMT solver from Lean. And the whole magic is thanks not to us, but thanks to an external lab, actually, like the lab at Stanford, that knows how to do the translation between higher order logic of Lean and first order logic of SMT leap through techniques such as monomorphization and whatnot. So this is what SMT does, and in this case, it succeeds. So the reason why we have this squiggly line and says declaration uses sorry, which is Lean's for admit, is because we actually trusted the SMT solver. So when the SMT solver said this statement is false, we said, okay, we believe you, which is what many people are pretty much okay with, like everyone who uses automated tools. People in the interactive theorem programming community usually like find this like very dodgy. And well, I have something to say about that, but well, hold with me. So obviously, I mean, you don't have to believe that what I have shown you is legit, because maybe I have just scripted all this underneath. So let's, I don't know, like let's just mess up with this protocol. Let's say, if, well, something that is definitely true holds, make yourself a leader. And you see what I've done. So now effectively anyone is a leader because this condition is true. Well, luckily, we can go here and see that it's no longer true. And it even gives us a counterexample, which is like, frankly, could be better. And in some more characteristic cases, we do pretty fine of these counterexamples, but well, this is a research tool, so if someone actually needs badly, we will do that. So, or maybe we have already done that, so it's just like my students need to update me on that. But this is a version as of, we have it on the branch. Yes, okay, so if you use a newer version, you will have it. Good, okay, so at least you see that I'm not bullshitting here. So okay, let me do something else. So okay, I just changed it to true. Let me change it to this. Will the property hold now? Yes. Okay, it's nice to be in the right crowd. So there is no awkward silence, so people know how to deal with like vacuously true propositions, because that's how the implication works. No one is ever a leader here. because last time I checked, it's very difficult to make one equal false if your theory is consistent. And indeed, it does work. How could we find it at the level of design? Because obviously this is made up, but what if I just made a protocol which at some point runs into some false conditions and certain execution branches never happen? Well, that's more like a liveness property, but in fact, if we think about the finite executions, then maybe we can make a hunch about it and cast it as a reachability property. So how about, so since we know that if we have 3 nodes, and one there is a scenario in which one message makes the full round, which is only three transitions, and it will become a leader, and some node will become a leader, right? So it's not necessarily every scenario, but there is a scenario with 3 nodes where after 3 transitions from the start, there will be a leader. Okay, so how about we try to get this angelic scenario and make sure that it's possible? So for that, we actually have another thing, and this example, we'll say, okay, let's start from 3 nodes, and after we do one send and then receive, 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 there should be a situation when there is a leader. And it says, nope. It's actually unsat. What does it mean for us? That means that the situation when we have a leader in the system of just 3 nodes after 1 send and 3 receive is unachievable. Why? Well, precisely because I make it so. So, and this is where we are. So, and now I'm going to change it back to the protocol and make sure that both my finite depth safety property and also my reachability property holds. And actually here, we, even in the version that I'm showcasing here, we do make problem model minimization. So what you're seeing here is actually a concrete example of the execution with all these 3 states in between. I mean, you need to have a little bit of training to read it, and luckily in Lean there are lots of nice things to visualize, so the sky is the limit, but you can see that we actually have a concrete example of how that is going to happen. You have the exact trace. You can rig the SMT solver to give the concrete traces of execution, which, again, something quite well known in the community. Just the nice thing that now we can do it all, not from a bespoke tool, which wraps around SMT solver, but from a proof assistant. So far, so good? Well, okay, I'm not going to stop here. So I'm actually here for the full-blown verification of this protocol. So to make things slightly faster, let me comment these 2 properties so we wouldn't have to recheck them every time we check something, we change something up above. So I'm going to go and I'm going to check that this invariant holds. So meaning that if I start from any state which already satisfies this property, and I may take one of these transitions, this property still holds. So you can think of it as a proof by induction. So we need to make sure that this invariant holds in the initial state, and it's closed under every transition. And if this is the case, then this is what mathematical induction teaches us. This property would hold at every reachable state of the system, because this is how you get to every reachable state, starting from the initial one and taking each transition. So far, so good. Well, this is not the case, because even though this property is true, it's not inductive. So it's too weak as an induction hypothesis. So if we just assume that we have a state in which this property holds, and we take an arbitrary transition from this state, this property might no longer hold. And this is called spurious counterexample to induction. And this is something that you will have to deal in your favorite proof assistant if you try to prove something by induction, but your induction hypothesis is too weak. And at this point, we usually use all our proficiency to start strengthening our induction, or in this case, starting to strengthen our inductive invariant of the system. The nice thing is that thanks to the SMT in the loop, and again, this is something that the tools like Ivy are particularly good at doing, we can have counterexamples that give us some idea why our induction hypothesis has been violated. And if you think about, can I make an invariant synthesizer with this thing? Rather than having a human in the loop? Yes, this is very much what is happening. So every OSDI and or SSOSP conference in the last few years had a paper about making a synthesizer over by generalizing the counterexamples. Okay, so I'm not going to talk about invariant synthesis since I already know what the invariants here are. I'm just going to use this really cool feature of Lean support in VS Code where you can pin this line, and I'm going to change the text above it, but the effect is still going to be displayed as of me having the cursor on this line. So I'm going to go and start strengthening my invariant by adding more conjuncts to it. So I've added one more conjunct. It didn't help much because because these two conjuncts are still not closed. Their conjunction is still not closed under this transition. So I'm going to add one more. This is already better, but we still have some violation. And finally, with this one, we have everything. So what does it mean? That means that we found the strong enough induction hypothesis that not only it's closed under all these transitions, it also implies these safety properties. So the conjunction of all these properties holds both in the initial state and both is closed after every transition. And I didn't have to write a single line of proof for that. Well, I could have, because again, this is the whole point. So this is very much the experience that tools like Ivy give you, but the problem is that SMT solvers are known to be quite brittle. So if God forbid you go outside of the decidable fragments, which are like relatively finicky, of the first order logic, or you have a part of the property that you want to prove interactively, well then, well, tough luck. So let me show you what kind of experience you want to have. So imagine that I want to have some extra insight of why my invariant is not passing. Remember, everything that we prove here is just a lean theorem. And SMT is just one of the, well, means of automation. It's just one of the hammers. So one thing that we can do is to ask the tool to give us only those statements that it failed to prove using SMT, for which we have this macro, after which it generates this theorem. And this is exactly the verification condition that it has tried to prove using SMT and failed. But what you're looking at is just a theorem in lean. And if you want to get extra insight, or you don't believe that SMT, because SMT might have timed out and you don't believe its result, you can just like start writing your regular lean proof script. And if you wish to discharge this verification condition interactively, by all means you can. Even more so, if at some point you manage to simplify it down to something that looks like SMT should be able to like make a quick job out of it, you can do so. Because again, this is just about using different means of producing your proofs together. I'm not going to be able to complete this proof because obviously that's not going to hold. My hypothesis is too weak, so I'm just going to roll back. But the last thing that I want to show in this demo is that even when we have everything verified and we get all the green marks as we want them, why it doesn't show? I minimize this thing. Thank you. Yeah, okay. So it's difficult to think and narrate at the same time. Okay, so even though we have all the green marks, we have this pesky, squiggly yellow thingy saying, trust in SMT solvers for 12 theorems. Wow, this is unthinkable. I mean, that shouldn't be the case. Okay, what am I doing? Okay, CAF would actually have no problem with that. So they would cheer. So the nice thing is that we can actually have the proof reconstruction turned on, which is not something that works 100% of the time, but it works a relatively high percentage of the time. And this is, again, not thanks to us. This is thanks to a lean SMT. And now we can go ahead and we can start proving things exactly the same way. So this is just a different syntax. Here it looks more like a proof script, but here it uses more fine-grained tactics such as solve close, which is what packaged all together in this check invariance macro. So the nice thing, and we can even do check invariance, I believe. So that one will not work, no? This one. Okay, thank you. Okay, so why is it blue now? There's no trust. Okay, so you don't trust the SMT solver now. Why? Well, because you actually have a proof term constructed by it. If for whatever weird reason, I don't know, you like looking at proof terms in lean, I'm not a fan, but who knows? It's a big audience, well, here it is. So this is what you're getting out of lean SMT. And well, now it's fully certified. Okay, that wraps up the demo. Any specific concerns about what I have shown before I proceed to the, I have 1 hour, right, for this. So I still have like 10 minutes to talk. Yes? Yes. Well, because you're saying there might be an execution in which I don't end up with a leader after something. Not sure I understand the concern. So. Okay, so here, right? Is that line number? Yes, yes, yes. This one. Yeah. What about this? So yeah. So you're asserting that there are at least 3 nodes. No, I said it exactly 3 nodes. Oh, at least 3. Okay. Yes. Okay. Sure. But that actually doesn't make a difference. So the more nodes means that I give myself more freedom. So it actually models the protocol with yes, at least 3 nodes. Yes, but that asserts that there exists a scenario in all systems which have at least 3 nodes. There is at least one scenario, which probably will involve exactly 3 nodes, where this is true. So this is the. Yes. Yes. Yeah. Yes. So SMT solver just finds us, example. I mean, this one, as you can see from the model, has exactly 3 nodes. That's a good question. Let me try it. And this is a dangerous territory when you start fiddling. Oh yeah, it actually does work. So look at that. So you're not really proving that in general this protocol will. No, this is symbolic testing, if you wish. So you can think of it as me asking, is there a possibility that in some way this protocol reaches the state where there is a leader after performing these actions? And I leave many things unspecified, so this is actually up to the SMT solver to find the instances for those. Great question. Nice to have the actual implementers of the tool in the audience, so I can give more interesting demo. Okay, moving on. Okay, so obviously I have very optimistically thought that I would go faster. So just to summarize what I have shown, and I'm going to skip through the major part because that goes about the meta theory of whale, which I'm delighted to discuss, and it talks about the extra monads and whatnot, and how exactly all these things is compiled underneath using some interesting semantic shenanigans. But from the user's perspective, this is effectively what we care about. So when you define a protocol state in whale, you consists of uninterpreted types and relations. You can actually include interpreted types as well. The point is that it will make your life more difficult if you want to use an SMT solver. But again, you can always have a fallback mode with an interactive proofs. So actions update this parts of the state which are mostly relations, and the invariants are verified to hold under all actions, either via SMT or interactively. And you can test reachability or safety symbolically using SMT. Okay, so what I was planning to talk about is the details of the implementation, which has to do with how we generate verification conditions. So, okay, in the spirit of bad practice of giving presentations, I'm going to skip through most of that and effectively only say that there are multiple semantics that you might care about. So how should we interpret those actions? So we can interpret them as, so I have 40 minutes or 1 hour? 1 hour, okay, yes. So we can interpret them as imperative programs for which we have weakest precondition calculus, and then the semantic of our programs in Veil is effectively the weakest precondition predicate transformer. So it starts from the post condition, you run it backwards through the program, and you get the predicate, which is the weakest precondition. So this is what should hold in order for your post condition to be true. How would you plug that into the invariant verification? Well, this is how. So effectively, you know that if you want to have the invariant hold after the initial transition, the weakest precondition should be true. And if you want the invariant to be inductive, you know that if you assume that invariant, that should imply the weakest precondition of any action with regard to the very same invariant. So again, this is not something particularly difficult. And the last one saying that your invariants collectively imply what you want to have as a safety property. The point is that if you want to do this thing that, well, someone in the audience was wondering about, which is this symbolic reachability check-in, this semantic is actually not really great. So what is great is another semantics, which is this one. which is much more familiar to people who think in terms of TLA plus, or big step semantics if you want, saying that my transitions are relations between the initial state, the result, and the final state. And you may forget about the result, just think about this initial and the final state. So we have these two semantics, and they are different. And turns out that both of them are expressible. The problem is that one of them is really well behaved with regard to SMT, and another one is really badly behaved with regard to SMT. So actually, the way we want to express the semantics is through another one. And after digging a little bit through the literature and probably rediscovering a bunch of wheels, we have figured out that this is how you should express it. So saying that this big step relational semantics can be expressed through the weakest precondition semantics where your postcondition is in fact this. There's a postconditions that excludes the result and the state that you want to get and negates that. So again, says like the results and state that you want to get are not unreachable from your initial state. Yes, so I see people shaking their head, and that was exactly the reaction that we had internally in the lab when we came up with that. So obviously you don't have to believe that. Well, the nice thing that we can actually prove the equivalence between these two semantics, and this is a nice thing of having things embedded into foundational proof assistant, is that your verifier can itself be verified. So we can switch between these two semantics at will, depending on what kind of verification we want to do for reachability or for safety property preservation, and we know that they are equivalent. With a small caveat that that only holds that if your action doesn't have crashes. So there is no assert false in the middle of it. So having exceptions in the semantics makes it even more interesting, because what to do with a transition that always crashes? Because if it just crashes, it means that it's not never taken, so it's a good thing, we can just exclude it. But on the other hand, this is a transition that blocks you from possibly reaching some states that you want. And well, after scratching our head even more, we realized that this is actually all part of even a larger picture, where this different treatment of exceptions can be expressed quite uniformly, but this is not the part of this talk, and this is something that we'll be happy to discuss offline. We have an upcoming conditionally accepted pop-up paper about this exactly. Okay, so to summarize, well, this veil is embedded in Lean, and we have the verification condition generators implemented in multiple possible ways depending on our verification goal, and the consistency of those VC generators between each other is still verified as a theorem in Lean. So finally, the last 5 minutes, I'm just going to very briefly mention case studies. So we took many case studies from Ivy. This is actually where I'm going to bring some bad news. The tool is really slow comparing to unverified tools just based on SMT. So the red thing is Ivy runtime. So Ivy is the main competitor tool, which doesn't have interactive proof mode, and it's not foundational. It's really thin wrapper written in Python over SMT solver, and it's like faster from like an order of magnitude to like, I don't know, like half, and only in a couple of relatively small case studies somehow we are faster than that. The interesting part is that the reason why Ivy is so much faster is that because we lose a lot of time doing the translation from higher order logic to first order logic. And in many cases, the queries we generate are actually not that bad. So this is something that might be interesting to the community, is that if we want to have a good SMT support from interactive theorem provers, well, there is certainly more work to be done about how to perform monomorphization and other translations. So the interesting part about these case studies are a few efforts that we have translated from different papers, which use the hybrid combinations of the tools. For example, Juliana Loza and Mike Dotz, I don't know if some colleagues from Galo are here, verified a protocol in a combination of two, of Ivy and Isabelle Hall, by proving some theorems in Ivy and some in Isabelle Hall. And well, turns out that, yeah, that was all correct, except we redid it all in Lean, and now we know that it was all correct, even though they had to do this translation. Some other paper actually was not so lucky. So there is an SOSP paper which had a formalization in Ivy and Rock. Really should have changed the slide. That was before the tool was renamed, sorry. So, and there, it turns out that the part of formalization has been done, okay, so, and the part was done in Ivy and part was done in Rock. So this is this paper. And what we found out is the invariant has been verified essentially in 2 steps. So some part of it, one conjunct, has been verified to be inductive in Ivy, so which is very good in dispatching goals in first order logic. The other part of the invariant that they wanted to prove was not in the first order logic, so they couldn't immediately prove it in Ivy, but turns out that this part was implied by the red part. So they ported the red part from Ivy into Rock and verified this implication in Rock. And sure enough, there were typos when doing this porting. And something that we have discovered because, well, that's the benefit of having one and the same system. Okay, I don't have that much time to grill you over this discrepancy here, but if you notice that here, PSAC is a successor of SAC, and this stands in one of the assumptions of this theorem. And here we say that if it holds over the, so here it holds over the successor, but here if it holds over successor, it also holds over P. So this is what they wanted to have, and this is what they included as, this is actually what holds true, so it holds over the successor, but this was included as an axiom. So it effectively holds over predecessor. And that's highly domain specific, and this is a small typo, but that's something that changed the whole course of the proof of the property that they wanted to have. Luckily, the property still held true. So, but that's the benefit of having the same thing in the unified system. Okay, so with that, I'm approaching the conclusion. We have lots of things to do. We actually are very close to having a full-blown T-style model checker, where you not only can symbolically verify, but you can actually run things and do all these TLA plus puzzles. So we are looking at the better generation of SMT queries to speed up the symbolic part. And in the long term, we're also thinking about doing the Iron Fleet style proofs between the Veo models and more realistic implementation in Lean that you can deploy and run. Lean is a pretty decent programming language. Lean itself is implemented in Lean. And we also are developing a library for composing and implementing Leibniz proofs, which is similar to what we have done before in Rock, but this part is yet not supported in Veo. And just to take away, what I've shown you is a Lean library for multimodal, i.e. automated interactive verification of distributed protocol in Lean. It's a shallow embedding. It takes full advantage of Lean as a programming language. It's foundational because verification condition generators are verified to be consistent with each other. And it has reasonable performance when it comes to automation, but also gives the seamless integration of interactive proofs. That's all I have. Thank you so much.
Questions?
Yes.
Hey, Ilya. You tempted me away from the distinguished papers session, and I'm so glad you did, because it was a great talk. Okay, so I have a question. You mentioned that, you know, a thing that TLA plus doesn't do well is actual verification, right, as opposed to just model checking. Another thing that TLA doesn't do well is it's not an actual implementation that you can deploy, right? And there's not any connection between your TLA model and the thing that you deploy, right? So maybe you sort of answered this question already in your future work slide when you said you wanted refinement proofs, right? But I guess that was going to be my question, right? Like a thing that Veil does not do today is actually connect proofs to runnable code, I think. Right?
That is correct, if I can start the response. Thank you so much, Lindsay. Yeah, that is correct, although Veo gives you exactly what is the high-level verification layer of Iron Fleet did, which is defining the state transition systems and proving the safety and hopefully the liveness properties. The next thing that we are planning to do, and I think we have all the tools in place with the stuff that I didn't present, is to make those models to be the ghost code for something that you actually run and prove the refinement through the manipulation of the ghost code and ghost state.
So you would have to like write another real implementation.
That's right. That's right. Sky is the limit. If you want to do deductive synthesis of something runnable from this, I would be very excited to explore that and collaborate. Well, this is possible. Yeah, absolutely.
We have 2 minutes. So
Yeah.
Hi. So a lot of times when you're designing a distributed system, you want to kind of like modularize it, so have some sort of underlying network layer that gives you guarantees, like maybe causal delivery or something. So in this language, have you looked at like how to modularize definitions like that?
Yeah. Great question. The short answer, yes, we have, and we don't have it yet, but we have a very good idea how to do that. More technically, this is something that you would do through sort of assume guarantee relations. Ivy has done that, and in Lean you can do that through the mechanism of type classes. Well, stay tuned, that's all I can say. But
Okay,
we very much recognize this, the need for modularity. Philippa, I think that should be the last one, right?
Yeah.
Hi, Elena. Great talk.
Thank you.
So in Rock, we know that, for example, you can do SMT-lib inside Rock, and so you've got a connection out to the SMT solvers through that mode. I don't know enough about what's going on with Lean. Can you say a bit? I mean, do they do a similar sort of thing?
Yeah. Okay. So the question is about how exactly bridge to SMT is supported with for Lean. Actually, I have to admit I don't know how SMT Coq does nowadays. It's been a while since I tried to use it. It was very brittle. In Lean, the tool that does
so at the moment, I think it's only on the Booleans and bit vectors.
Okay.
So
I see.
And
Okay.
that's all they needed.
Yeah. So I'm not an expert here. So Clark Barr's group has a fantastic paper at this CAF this year on Lean SMT, the tool. And what happens is that for CVC5, they sort of make SMT solver to reproduce a trace that they then render consistently into the proof term of Lean, which you can interpret in Lean, and after that you can check that this is indeed a proof of the theorem you want. So it's you can think of it as a translation validation done for the SMT solver.
Thank you. And also sort of a bit related to this, which is in our sort of world, is this, I haven't seen anything like this in Lean before. Have you sort of basically shown this two-world thing, or are there lots of other examples?
I think we're the only game in town. So
I think so. No, but I think so too. But
at least according to Lean FRO, Stanford, Amazon, and Google, they haven't seen anything like this. So we showed it to all of them.
Well, it shows it. It's
Thank
cool.
you.
Okay, so let's thank the speaker.
Okay.
Yeah.
You can just in your bag or somewhere.
Yeah, in my pocket?
Yeah.
Okay.
It's good. You can't do wrong. And if you like to speak.
Yeah. Yeah, it's good. No, I'm Julien Lehmann. I'm French. Okay. No, but you, yeah.
Testing? Yes.
Okay.
And our next presentation is by Julien Lehmann.
Yeah, thank you. Today I'm going to present our work verifying neural networks with pirates. which is a tool we developed with my colleagues at CEA, Augustin Lemel, Tristan Legal, and Zakaria Chiani. So this is quite different from the other talk. It's based on AI, it's verifying AI. As you may have noticed, everybody talk about LLM and use AI, but they are also used in critical systems such as aeronautics, nuclear energies, health, and as such, they should be treated the same way as classical software used in a critical system, meaning they should be tested and validated. That is why we created our tool, Pirate. So, Pirate is verifying a certain type of architecture of AI. It's called neural networks. Basically, it's a succession of linear and nonlinear functions. Usually, the linear functions are matrix multiplication or convolutions, and the nonlinear functions are generally element-wise real functions, which are classical functions are the ReLU, the maximum between 0 and x, and the sigmoid. This is an architecture that is called layered. And now that is the thing that Pirate will try to verify. The property we are considering is a global safety property. So given an input set and an output set, we want to apply the neural network to this input set and verify that the output set is the output set of the neural network is within the desired output set. We also consider a second type of property. It's called the local robustness property. You are given an input and a perturbation gamma, and you want the prediction of the neural network to be the same in the gamma neighborhood of this input. So this is basically what is used for high-dimensional non-structured data, such as images. How do we do that? So first of all, verifying neural networks is something that is hard. Indeed, it's an NP-complete problem for ReLU neural networks. So what we do is using abstract interpretation. In neural networks, what we do is that we have our property, which is the input set. We transform the input set with the first layer. We over-approximate this whole set, which gives us an approximate set, and we repeat this process, and we obtain an over-approximated output layer, which output of the neural network, which gives us three cases. Either you are in the entirely contained in the property, which means that you have proven your property. If you are entirely outside, it means that your property is false. But when you are in the case when there is an overlap between the two, since you are considering over-approximation, you cannot conclude. So Pirate, which stands for Python Reachability Analysis Tool, takes into input three files: a property file, a neural network file, and a config file, which contains numerous different options for Pirate. There is some processing steps and some analysis steps where there is the reachability analysis, where we perform the abstract interpretation. So neural networks are represented. There is different formats. In Pirate, we support the main format, which is ONNX. We have also other formats, but this is more limited. We take these formats and transform them into our own internal representation of neural network to efficiently verify them. There is some operations are slightly modified to improve the efficiency for the verification later. And same for the property. There is one kind of format for the property. This is called the VNLib format. We also design our own format for simplification to define a property, which is just access for the inputs and Y for the outputs. So with this, with this input set, we can perform abstract implementation. In Pirate, we implement many domains, intervals, symbolic intervals on the top, polytop, constraints on the top, hybrids on the tops. I'm going to talk to you about intervals on the tops and constraints on the tops. Keep in mind that while doing the over approximation with all these functions, Pirate is sound with respect to floating point operation, which is not something that is common with for the other neural network verifiers. So to illustrate these abstract domains, I'm going to use a toy network and property. So you have this little neural network. The property is you have x1 and x2 between -1 and 1, and you have to prove that the output is between -1.8 and 2.5. So for the intervals, it's just classical interval arithmetic, but just to quickly walk you through it. So you perform, for the top row, you perform 3 times -1, 1 plus 1 times -1, 1. You obtain -4, 4. The ReLU, you apply the ReLU to -4, 4, which is the maximum between 0 and -4, 4. You obtain 0 and 4. Same for the bottom row. You add them up. You obtain that the output is between -3 and 4, which is not enough to conclude. Thus, we need a more precise domains. So, sonotops, these are, if you are familiar with it, good, but if not, a quick walkthrough is that it is an affine transformation of an hypercube. It is represented by 2 parameters, parameters alpha and beta. You need a critical operation is the concretization. It's to transform it into an interval, because at the end you want to know if your property is proven or not, and you need to have bounds. This is easily computed for the sonotops because it's just the L1 norms. And you also need the concretization operation to over-approximate non-linear function, because the sonotops is an affine form, and the non-linear functions are by definition non-linear. You need to over-approximate them to represent them. So the sonotop approximation of the ReLU, you need to have to add a new dimension to your hyperbox, to your hypercube, and you have new alpha prime and beta prime, which depends on the lower and upper bound of the concretization. So on the example, you get the result that the output is x1 over 2 plus epsilon 1. Epsilon 1 is the noise introduced to over-approximate the ReLU 1 minus 3 quarter, which is the same from the ReLU 2, plus a quarter. So now the output is between -2 and 2.5. It is closer, but still not enough. And for that, in Pirate, we have the constraints on the top, which are the sonotops with affine linear constraints. So for the ReLU, since it's just the maximum between 0 and x, we just had the constraint that the ReLU is positive, and the ReLU is greater than x. With this constraint, now on the toy example, it creates 4 constraints, and now this is enough to prove our property. But what if the property was harder? What if our abstract domains were not enough to prove the property? A simple thing to do is to perform multiple analyses to have tighter bounds. So this is called branching bounds on inputs. So you just, instead of taking between -1 and 1, you take the first one to be between -1 and 0. You prove that, and you do the same for the other part. You prove it. Now it's easy to parallelize, and we can leverage GPUs. But this is something that scales with the number of input dimensions. So this is hard to verify in practice for high input dimensions. So we have a second thing in Pirate to circumvent that, is to split on role use. It is a nonlinear function, but you can consider it either to be, if you are in the negative case, you only consider the role use to be 0, and if you are in the positive case, it is just the identity functions. So these are linear constraints, so you can handle that with constraints on the tops. And similarly to branch and bound on inputs, you can prove them. You can also parallelize them and leverages GPU. But now this is dependent on the number of role use and not on the number of inputs. So this is the overall mechanism of pirates. But with this multiple analysis, you will be able to falsify your property if it is false. But what we find more efficient is to have a counterexample search strategy. So we just define a distance and we minimize that with some optimization, so that when we perform multiple analyses, at the end of each reachability analysis, we run this algorithm to try to provide us with a counterexample. Now that I have presented you with all that is done in Pirate, how can you test and evaluate Pirate? There is an artifact available on Zenodo, and for research purposes, you can contact us and we'll provide with you with a free license, because due to politics at CA, our code is closed source. But once you have your license, the installation is really easy. You just get all your packages with peoplestyle and you are ready to go. So just to highlight some of the capacity of Pirate, there is an annual neural network verification competition. So we participated in the last 3 competitions. We each time got the podium. There is a large range of neural network that is tested in this competition. As you can see, input dimensions are ranging from 1 to 1 million. The number of parameters in the neural network are ranging from 500 to multiple millions. So our tool is really competitive. I just want also to show you a quick illustrative use case. So this is from a joint work with Airbus. There is a paper on it. So they had drones, and they had lookup tables that for each value in the lookup table that said if there is an intruder in this zone, you have to either go left or go right or go straight. But these tables were 30 gigabytes, and these tables were supposed to be embedded in drones, but they took up too much space, too much memory. So what they wanted to do was use neural network, but they needed to certify the neural network because they didn't want their drone to crash. So we managed to prove that 85% of the neural network matched with the lookup table. So they built a hybrid system with 85% of the neural networks and 15% left of the table. It went down to 5 gigabytes, and that could be embedded in drones. So with all that, we still have many things to do on Pirate. I just shown you that we are splitting on ReLU, but we are not actually able to split yet on other nonlinear layers, such as the sigmoid functions. There is also an ongoing effort to handle other AI architectures, such as transformers and RNN. And we are also trying to address embedded AI systems with our work with the edge platforms. So, meaning that we are trying to handle better the integer and floating operation. Thank you for listening.
Oops. Okay. I am not entirely clear on the way you do the splitting. So I understand that you try to identify the branching point, which I see fairly well how it would work for the first layer. Now, if you have, say, 5 layers and you want to do this on one of the last layers,
so
do you do
you
some
mean
kind of
for
backwards?
the ReLU, you mean?
Yes.
Yeah. Okay. Actually, we can do indeed everywhere. If I remember correctly, there is indeed what we are using is that we are using some heuristic to have a score to determine which ReLU do we want to split. Same for inputs, we have a score to determine which is the best to split on. For the ReLU, it is quite similar to the input. Is that we have a heuristic that score with the noises that are introduced, because what we interpret is that epsilon1 represents kind of the effect of the over approximation of the ReLU. So whichever of the coefficient is the bigger in the last in the output, we consider the split. Well, there is also some other operation done to perfect this heuristic, but the gist of it is that. So it's not always on the first layer or in the last layer, but if I remember correctly, I think it's most of the time kind of the first layer.
I see. Okay, actually, behind my question, I was actually wondering whether you would have cases where you want to you should do some splitting with respect to, say, the third layer, and that would get you to do more splittings on the second layer and then in turn to the first. But I don't think this seems to be happening, right?
Well, just to be sure, you are saying that if we split in the later layer,
whether splitting on the later layer would let you infer more adequate splittings on the first layers, or whether it's just one pass.
I think on that point, you are right.
Okay. Yeah. Thank you.
Thank you.
Any other questions? I do have a simple one.
Yeah.
At the beginning, you said that there is L plus 1 linear functions and N non-linear functions.
Yeah.
So, what's the typical size of N?
It's true that it really depends, but generally, I don't think we have like L bigger than 30 or 50. It's never more than that. But it can be just, if L is 1, yes, it just in the competition there are some network where the L is just 1, so just a linear function, a non-linear function, and a linear another linear function. So a small networks. But yeah.
And is there always one more linear function than non-linear? That's a given?
Well, it's just the way I presented it. We handle kind of other things, but it's just a neat representation for the definition.
Thank you. The next talk is still about neural networks, and Tom is hailing from Technion.
Can you hear me in the back? Great. Okay. Good afternoon, everyone. My name is Tom Uviler. I'm for the Technion Israel. And today I will be presenting our paper about enhancing neural network robustness via the synthesis of repair programs. Or in other words, how can we leverage program synthesis to defend against adversarial attacks? This is a joint work with my advisor, Dana Drexler-Cohen. Let's begin with some background about adversarial attacks. Consider we have a pre-trained neural network, as you can see at the top of the slide, that given an input image of a cat, it correctly classifies it as a cat. Now let's consider a different scenario when we have some adversarial attacker that adds a very small, imperceptible noise to the input image. Usually, this noise is bounded by some norm, such as the L2 or the L infinity norm. And now, almost the same image, which also looks for us as a cat, is actually misclassified as a dog instead of a cat. This raises the important question of how can we defend against such attacks while maintaining the high clean accuracy of the original unperturbed images. So, in this work and in other works, we want to develop an adversarial defense that maintains the high clean accuracy, which is the accuracy on the unperturbed images, and to provide high robust accuracy, which is the accuracy on the perturbed, adversarially attacked images. But we also have other objective, which is to make our defense to scale to large real-world neural networks, and we want to keep the training overhead, if needed, and the inference overhead relatively low. In the next slides, I will present some of the current approaches for adversarial defenses. The first approach, and probably the most common one, is adversarial training. According to this approach, we train the classifier on adversarially perturbed inputs together with clean inputs. As you can see here, we have a data set of cats and data set of dogs with the benign unperturbed images and with the adversarially attacked images. And actually, this often improves the robust accuracy with zero inference overhead, and it also scales very good to large networks. However, the main limitation of this approach, as you can probably guess, is the high training overhead, because this training process is an iterative process. As the network weights are updated, we generate new adversarial inputs and train on them the network again and update the weights, and so on and so on and so on. So we have a very high training overhead. The second approach for adversarial defense is randomization. In general, adversarial attacks are not just some random noise that we add to the image. They are carefully calculated perturbation, which the attacker designed to flip the prediction of some input. So the idea in this defense is to add noise to the input or to the classifier by adding some random layers, and in this way to mask the carefully calculated adversarial attacks. A popular framework for this approach is the randomized smoothing defense, when we add noise to the input and to the classifier, run many instances of the input through the classifier, and decide about the final label by a majority vote. So while this scales to large network and has high robust accuracy, it has two main drawbacks. The first one is the inference overhead, which is relatively high, because for every input, we need to run through the network many instances, noisy instances of the same input. And in practice, it doesn't, it really hurt the clean accuracy, since we're adding noise to the classification process. A third approach for defense is the post-training repair, which usually has two steps, as you can see in the slide. The first one is to detect the weight that caused to the misclassifications or any other undesired behavior. And second, the second step, based on the first step, is to adjust a small set of these weights and to repair them in order to increase the robustness. In practice, both steps are really challenging. It's very difficult to pinpoint the exact faulty weights out of millions of weights, and to find the right repair is also very challenging. So as a result, many of these repair methods do not scale to large network, and the improvement in the robust accuracy of how can we defend against adversarial attacks is pretty modest. So in the next slide, I will present our approach for adversarial defense, but I want to give you a very short background about image classification with neural networks. Typically, the classification process in these networks begin with some input image that we pass through the encoder to obtain a feature vector of some dimension m, and then we take this feature vector, pass it through the classifier, and we get the output vector, which holds the score for the C possible classes, from which we select the one with the maximum value. What we suggest is to defend against adversarial attacks by integrating short repair programs, as you can see in the center of the slide, into the classification process. A repair program takes the feature vector as an input and repairs it. You can think about it conceptually as reversing the effects of the adversarial attack, and it outputs the feature vector, which is then passed through the classifier and to obtain the output vector. Before getting into the details, I want to give you a short intuition about why this approach might work. So at the top of the slide, you can see the median absolute change of the latent feature under an adversarial attack. As you can see, only few features are massively impacted by the attack, while the other are less impacted. So this gives us the idea of maybe we can fix only few of the latent features in order to increase robustness. If we zoom in onto the first 10 features, we can see that the feature number 4 is highly impacted from the attack, and feature number 8 is far less impacted. And if we take a look at the correlation matrix at the right bottom, we can see that feature number 4 and feature number, here it's 7, should be feature number 8, are negatively correlated. So it gives us an idea of we can repair the fourth feature with feature number 8 by multiplying it by some negative constant, and then we can mitigate the effect of the attack without changing the computation of the networks too much. So now let's discuss how can we synthesize these repair programs. Our repair programs are composed of a sequence of assignments to few of the components of the feature vector. The right-hand side of each assignment is based on a simple arithmetic and comparative operations involving constants and the features themselves. The output of the repair program is the repaired feature vector, which is then passed through the classifier. At high level, you can think about it as like a small algebra on the latent space. The syntax is pretty simple and straightforward. Each assignment targets only one feature, VI. On the right-hand side, we place either a number or a constant, or another feature, or an operation between these two data elements. So we can say set VI to the value of Vj plus 0.7, or set Vi to the constant 0.5, or any other calculation that you might think of. This domain-specific language is pretty simple, pretty straightforward, but we show it's actually quite expressive, and it's expressive enough for our repair programs. So far, I described a single repair programs, but in practice, for each data set, network, we synthesize a set of repair programs, which in inference time, we randomly select one of these program and integrate it into the classification process to repair the feature vector. This process makes our defense less predictable to adversarial attacker, which is an adaptive adversarial attacker that can can query the network multiple times and to learn our defense. So this process of randomization helps us to mitigate it. Now I will talk about our synthesis algorithm. We will start from the challenges. In practice, computing this program that maximize the clean accuracy and the robust accuracy at the same time is highly challenging. First, it requires to identifying the best neuron to repair and the best neuron to repair other neuron with. The program space is very large. We have a large number of variables to select from. So this is the first challenge. The second challenge is that there is no monotonicity between the effectiveness of a given program and other programs that extend it. And as a result, greedy synthesis of generating the next best instruction from a current candidate is unsuitable, and also stochastic synthesis that samples full programs is infeasible in our case, since the number of samples to converge is very high. So with these challenges in mind, we developed our synthesis algorithm, which we named DefenSyn, defending by enumerative stochastic synthesis. And I would like to highlight some key aspects of our algorithm. Our synthesizer uses an adapted form of enumerative synthesis to explore the space of the large space of repair programs, focusing on short and effective programs. Basically, it explores programs of increasing length, starting from programs with one instruction, then two instructions, etc., until some predefined bound. The synthesizer works and selects programs based on some score, which balances both clean accuracy and robust accuracy. To help the synthesizer to converge to good solution, we learn distributions for the right-hand side and the left-hand side feature for each assignment, and it helps us to select better variables that can actually make our programs more suitable for enhancing the robustness. And lastly, if the selected programs we select are too similar in the set that I have showed you before, they might be predictable to the attacker and therefore giving him some advantage over our defense. So to counter this phenomena, our synthesizer ranks and selects the highest scored programs that have a diverse set of repaired features in the left-hand side of the assignments. Let's see a simple example of our synthesis. We start with a data set of clean images and their adversarial counterpart. We send them both through the encoder and extract the feature vectors for each image with its perturbation. And then we explore program of increasing length. In this example, up to length of 3 instructions. And for each length, we run the about 1 million sampling iterations. let's skip and say that we are now at we discover program of length 2, and we are at the last iteration, the 1 million iteration of length 2. We have distributions for the left-hand side and the right-hand side variable, and a valid constant, a range of constants and operations, which is the green boxes that you can see here in the slide. And we sample a program based on these distributions. And then we calculate the score of the program. We're using the feature vector we extracted earlier, and we modify the vectors according to the program, submit them to the classifier, and count how many are classified correctly. We also have a balancing factor, lambda here, that balances the clean and robust accuracy. In this example, lambda equals 1. After we compute the score of this candidate program, we update the program's dictionary, which stores the best scoring program for each diverse set of repaired features in the left-hand side of the assignments, as you can see in the slide. Okay, so now we move on to the first iteration of programs of length 3, here at the bottom of the slide. We update our left-hand side and right-hand side distributions based on the score of previous explored program. And again, we sample programs from these distributions, when the goal of updating this distribution is to direct our search towards more promising variable based on the score of previous programs. We calculate the score exactly as I mentioned before, and update our program dictionary. Lastly, we finished all our iteration for all the predefined program lengths. We select the top K programs with the highest score from the dictionary. Note that each of the selected, here K equals 3, each of the selected programs has a different repaired features in the left-hand side, which makes our set of repaired programs diverse. This slide shows the full framework of our approach. We start with a trained encoder and the classifier and adversarial attacks, and a small training set, which usually it's about a few hundred images, and we run defensing to synthesize a diverse set of repair programs. Then, at inference time, for each new input, we integrate one of these programs into the forward path, and it gives us robustness with minimal change to the original network. We evaluate our tool against several attacks on multiple large neural networks. You can see several attacks with different types, L infinity, L2, L0. As you can see, we achieve high clean accuracy and high robust accuracy, which we on average improved by 40%, with a very small inference overhead. Also in this large network, the synthesis time is about 1 or 2 hours, which is much less than the training time needed for adversarial training. We don't show here prior repair-based defense because they do not scale to these real-world large networks. So summing up, our paper introduces the first attempt to leverage program synthesis for adversarial defense. We show it scales to large network with good performance, low overhead, and that's basically it. Here is the QR code for the paper and the code. And thank you very much for listening, and I'm ready to take some questions. Thank you.
Any questions?
Thanks a lot for your talk. It's very nice. I have a question. If you were to use neural net verification in this setting, how would you verify robustness? Would you apply at the classifier level, or you would take your level as well? So have you considered using neural net verification on top of this?
Yeah, that's actually a very good question. because we show an empirical defense. We are thinking and we are trying to implement a verification that rely on these programs, because basically what we do is changing only few features. So if we can detect which feature we need to modify in order to achieve verified robustness, we can actually do it with our programs, but we are thinking about it, and it's really promising direction of research.
Thank you.
Other questions? So how do you know that it actually, oh, I'm sorry, there was one I didn't see. Please, go first.
Hi, great talk. Can you review the program synthesis, how it locates in the space of population-based optimization, like genetic programming or Bayesian optimization?
Yeah, can you repeat the question?
So, genetic programming and Bayesian optimization algorithms are in the broader class of population-based optimization. And is the synthesis here more straightforward than for a general optimization would be required?
Yeah, in some sort, it's kind of Bayesian optimization, because we learn the distribution through the process of synthesis. We try different flavor of this stochastic Bayesian search or optimization. This one is the one that we find that actually fits the best for our programs. But definitely we can use different flavor of Bayesian optimization as well in this, to search in this program space.
So the left-hand side and right-hand side, the distributions, that's the part where you do the stochastic modeling.
Exactly.
Thanks.
Thank you. Other questions? Completely naive one. How do you know that you repair and do not make it worse? How do you know that it actually repairs and does not make it worse?
In terms of clean accuracy.
How?
In terms of clean accuracy.
Okay.
That's actually a very good question. We have in the way we calculate our score, we take into consider the robust accuracy. We want to enhance the robustness of the network, the accuracy on the perturbed and adversarially attacked images. But we also have this component that actually give us some assurance that we will not make the network much worse. As you can see in the results, in the clean accuracy, it's true that without defense, with no defense, we achieve a better clean accuracy, but the drop by using our tool is really, really small.
And one last naive question. Suppose that now I know how you repair. Can I manufacture an input that, because I know how you repair, it will actually make things worse because of your repair?
Attacker. That's where our diverse set of programs comes into account, because for every inference step, for every forward pass, we select different program. It's really challenging for an adaptive attacker that can actually know what are the programs to predict what would be the next program that we use. So that's how we mitigate this kind of scenario.
Thank you very much.
Thank
and
you.
That wraps up our session.
Okay, so hello everybody. So good evening. So welcome for this last session for today for SAS. So now we are going to talk about abstraction and proofs. And the first talk will be about relating distances and abstractions with an abstract interpretation perspective. This is research work by Marco Campion, Isabella Mastroianni, and Caterina Orban. And Marco is going to give the talk. And before you start, I would like to congratulate you again for the Radiacuso Award. So please go ahead, Marco.
Okay, can you hear me? Yes. Okay, thank you, Xavier, for the presentation. So in this talk, I'm going to present our result about relating distances and abstractions with an abstract interpretation point of view. So I will start by saying that understanding program behavior in computer science is a key challenge, which is quite hard, of course. Why? Because most of program properties that speak about program behavior are undecidable. So we need to approximate. So we need to use approximations. In both, we need to use approximation in both the way we study programs, but also in the way we formalize properties of programs, so hyperproperties. Examples of classic hyperproperties that study the program behavior are non-interference in language-based security, robustness in machine learning, completeness in abstract interpretation, differential privacy, and so on. So broadly speaking, we can define two main paradigms of approximations. So a quantitative approach versus a qualitative approach of approximation. Quantitative approaches capture quantitative aspects of the approximation. So for example, by using distances. So in this example, we have a distance between image, which can be the difference in terms of pixels. While qualitative approximations can be considered as capturing semantic aspects of the objects. So by using abstractions. So the questions that we want to try to answer in this work is that, are these two paradigms of approximation orthogonal, or can in fact one be an abstraction of the other? Can one be derived from the other? Can we formalize a general approach to combine them in a unified way to approximate? So for our purposes, we will use the formalism of pre-matrix in the quantitative approach and upper closure operators in the qualitative approach of abstractions. So we'll introduce briefly the concept. What is a pre-matrix? It's not a metric, but it is a binary function. So it is a very simple distance that provides a distance between two objects, which satisfy only two axioms: non-negativity and the if identity. So whenever two objects are identical, the distance must return 0. So why they are called pre-matrix? Simply because they are among the weakest type of distances. As soon as this kind of distances satisfy more axioms, such as the symmetry, triangular inequality, etc., we can get other form of distances. So we can get quasi-semi-matrix, semi-matrix, pseudo-matrix, and then matrix, which should be one of the most used distance in the literature. So for example, we have the Euclidean distance, the classical one, which is a metric. Then we have the size distance, which measures the absolute value of the difference in the size of two sets, which each is a pseudo-metric. And if we focus on just sets that comparable sets, then we have actually a quasi-semi-metric. So the key idea is here that depending on what we want to measure with the distance, we can have different properties. And depending on the properties, we can have different results. By qualitative approximation, in our work, we use upper closure operators, so as the abstractions. What is the formal definition of an upper closure operator? It is defined over a partial order set. So it is simply a function over a domain, over a partial order set that is idempotent, extensive, and monotone. Usually, upper closure operators are defined by their fixed point. So the set of all objects such that the operator returns the same object. Why are important upper closure operators? Because they are quite used in APSA interpretation. Simply, they are equivalently defined in another way. So in fact, in APSA interpretation, upper closure operators are Galois insertions. Why? Because if you define a Galois insertion as an abstraction function, as a concretization function, the combination of the two, so if you combine the abstraction and from the concretization, you get an upper closure operator. As an example, we have with the interval abstract domain, where you have the abstraction function and the concretization function over the power set of integers. Then the upper closure operator is defined over the concrete domain, so the power set of integers, and it returns the approximation directly in the concrete domain. Other example, you can define whatever as soon as you are a Galois insertion, you can define the relative upper closure operator as this kind of a combination. So we have, from one hand, we have the pre-matrix. So here I will represent examples with arrows and weights. So if you have an arrow from x to y, it means with the weight 0, it means that we have a distance 0 between the two objects. And if there is no arrow, then it means that the distance is simply infinite. And on the other hand, we have upper closure operators. What I want to show here is that what we showed in our paper formally is that we have, in fact, upper closure operators can be defined as an abstractions in terms of Galois connections, as an abstraction of pre-matrix. By doing so, we do so by passing through equivalent relations. And in fact, we show that whenever we have pre-matrix that can represent upper closure operators, these pre-matrix are in fact a strict subset. So we call this an upper closure operator matrix. And I will show them later why we need this kind of abstraction process. So I want to show briefly this process from a distance representing a pre-matrix, converting it as an upper closure operator, so as an abstraction. So we start with the domain of pre-matrix, it's just the set of all possible pre-matrix on a domain, which is assume that it is a domain with a partial order. Then we have an ordering over the distances, which in fact is a way to say that a pre-matrix is more general, is more abstract than another pre-matrix, by saying that, for example, D2, in this case the definition says that D2 is greater than or equal than D1 if D2 represent objects with more objects with distance 0 than D1, or it increases the distance. So in this case, we have the distance between X and U, we have a 0 distance, so while the other distances are equal, so we can say that D2 is an approximation of D1. Okay, so starting from a pre-matrix, the first step is applying symmetry over the distance 0 of the object, so that we can have symmetry only on distances that have 0. Then we apply transitivity, so that we have distance is 0 between all the objects that they can be reachable between each other. And at the end, we construct an equivalence relation by a Galois connection. So there is a relation only between elements that have a distance 0. Then we continue the abstraction process by turning into an upper closure operator. So we need to force all the three properties of upper closure operator. So before we transform an equivalence relation as an extensive function through an abstraction. By doing so, we simply select a representative element in the equivalence class by taking the list upper bound. This is done again by a Galois connection. Then we apply an operator to force monotonicity. Here we use the construction from Couzeau and Couzeau, a paper from Couzeau and Couzeau from 1979, a constructed characterization over closure operators. So we force monotonicity with this operator. We force the property of idempotent to get also an idempotent function. And at the end, the composition of this process is again an abstraction through a Galois connection. So this is the overall process, very generally. So we started from a pre-matrix, and we get at the end an upper closure operator. What is this upper closure operator at the end that we had? Is that it corresponds to all the pre-matrix that recognize with distance 0 all the elements that has the same property. The property represented by the upper closure operator in this case. So the property that the pre-matrix has distance 0, while all the other distances are infinite. And in this case, we can see that all the abstraction process we get pre-matrix, which are a special kind of pre-matrix, which are in fact a subset of the standard of the pre-matrix where they started. So why this is important? Because what we want to do now is doing something that is very related to what we do in abstract interpretation. So in abstract interpretation, we combine abstractions to get a systematic way to define, to abstract the process of something like the behavioral programs, for example. So what we want to do now is combine distances. So here in this case, we combine distance 1 with distance 2 through an operator f. And what we have formalized here is that we can first apply distance 1. So that distance 1 actually, what we use about distance 1 is agglomerating all the elements that have distance 0. Then we select a representative element in this representation for each group. And then the distance 2 will be applied only between these representative elements. As an example, if we apply the distance that we obtain by applying an abstraction through an upper closure operator with another distance, so the upper closure operator rho, the abstraction, you can select any kind of abstraction that you want as a Galois connection. You just consider elements with distance 0. As a representative element, you can take the least upper bound of the class, and then you apply the distance between the representative element. So what you obtain at the end is a distance between the semantics approximation through the distance to the property rho in this case. So as an example of application, something very similar that was applied to non-interference. And it was called abstract non-interference, that it was published in 2018 by Giacobazzi and Mastroeni as abstract non-interference. So in this case, the property says that whenever we have two objects which shares the same property, and here the property is formalized as the upper closure operator eta, then the same property must hold in the output by applying f through another upper closure operator rho. So we have to, there is a form of indistinguishability with the outputs. So this is a parameterized form of non-interference, where the property where we are analyzing are represented by upper closure operators. So we can make this property weaker by considering a partial version where the output property is not simply the equality that we want to observe, but there is a distance between the properties that we are, the output property that we are considering. So as soon as we have looked at, you have used this combination of distances, as soon as we have the same distance, the same zero distance at the inputs, which means that the objects share the same input property, then in order to have a partial abstract non-interference, we must preserve the distance between the semantic approximation. And this distance must be at maximum epsilon in this case. So as a specific instance of this property, new property that we have defined by combining distances, is when we impose a distance 0 in the output. Well, in this case, whenever we are using a distance which is quasi-symmetric in the output, so it means that it is able to recognize this equal elements, then we have that the 0 partial abstract non-interference implies non-interference in this case. So we have a coincidence. As another example of the utility of combining this kind of approximations is that we are able to compare with other program properties in the literature. One example was abstract interference. Another example is about the completeness or partial completeness in abstract interpretation. Briefly, what is the partial completeness in abstract interpretation? So whenever we have a program to analyze, so we have a concrete semantics on the left, and an abstract semantics of the program on the right. So completeness is simply the equality between the two results, so between the concrete execution and the abstract execution. What requires instead partial completeness is that the distance between the two results can be also unequal, so could not be the same, but as soon as the distance is at maximum epsilon. So how we compare this property in abstract interpretation with the partial abstract non-interference that we have seen before? Well, we can simply slightly rewrite the property of partial completeness in abstract interpretation in this way, where in fact we are calculating the distance between the concrete execution and this kind of abstract execution, which is called the best scored approximation of the program P over the abstract domain identified by the upper closure operator rho. And so the final result by comparing the two properties is that whenever we have a proof of epsilon partial abstract non-interference of a program, then this proof in fact tells us more in the abstract interpretation framework. It tells us that the best score approximation of this program will satisfy an epsilon partial completeness property. So this means that the best abstract interpreter that you can build with over the abstract domain rho, it will have a maximum amount of imprecision determined by epsilon. On the other hand, if we can prove that the best score approximation of our program is epsilon partial complete, then we have also a proof of partial abstract non-interference by an amount of 2 epsilon in this case. So I can conclude by saying that we have proved that in fact abstractions defined in the abstract interpretation way by Galois insertion of upper closure operators in fact are abstractions of pre-matrix. And pre-matrix represents pre-matrix have a specific structure. The pre-matrix that can exactly represent upper closure operators have a specific structure. So we can apply in this case combination of distances and as we apply abstractions in the abstract interpretation. And why this is important? Because it provides a way to define a general approximation strategy. So that also we can then provide a comparison between program properties that are already defined in the literature, and we can define theorems, for example, as we have seen before, by saying that if we have a proof of program property, we can turn this proof into another program property. So this was the general idea. And that's it. Thank you.
Are there any questions? Otherwise, I do have a question. Actually, can you guess what my question will be? What if we don't have alpha and only have gamma?
Okay. Yeah, of course. So not everything is representable as a Galois connection or a Galois insertion. So we choose the Galois connection property because we have so thanks to this strong mathematical framework under the Galois connection, we can derive this way of abstractions. But as a future work, actually, we plan to provide a similar way of abstraction by using a weaker form of Galois connection that are defined in the literature, which admits also to not have an abstraction function alpha.
Thanks.
Yeah.
I cannot see your name.
Oh, thanks. Thanks for the talk. Maybe to be excessively concrete, if I give a simple example,
Sure.
If I have real numbers, right, I want to know, oh, okay, they're within some epsilon, but if I'm looking at it discretely, then whatever I'm doing with my upper closure, I assume here, would break them into equivalence classes, and it seems like those two views of abstraction are at odds in that. Does the theory you have here give me some way to deal with that question of abstracting the real numbers, or does it kind of is gnash against it in a nasty way. So I guess technically it seemed like maybe the pre-metric might be approximating in the wrong way there.
Exactly, yes. So yeah, in fact, we choose the pre-matrix formalization because the fewer properties that they require, in fact, allow this kind of distances to further approximate what maybe we can represent as a matrix. So I don't know if I fully understand your question, but the fact that in a way, we can further approximate something. So this is kind of typical in upstream interpretation where maybe we cannot use a specific matrix to measure, for example, imprecision of upstream interpreters. So what we do, we select distances suitable to our need that in fact are not matrix. And so what we do in this case, we are applying a further level of approximations, and especially in the case of where matrix are maybe applied to discrete domains. I don't know if I replied to your question correctly.
No, it's fine. Thank you.
Thank you.
Okay, thank you very much. Let's thank Marco again. Now move to the second presentation, which is about specifying and verifying future conditions. So, oh, sorry, no, I'm I apologize. I was looking in the wrong line. So we are at the second presentation, which is about precise abstract interpretation.
think sound works. No? Okay, so we are now going to move to the third presentation of this session, which is about specifying and verifying future conditions. So this is work by Yahweh Song, Darius Fu, and Wayne Ganchin, and Yahweh is going to give the talk, so please.
Right. Thanks for the introduction. Thanks for coming to the talk. So today I'm going to present you our recent progress on specifying and verifying future conditions. And my name is Yahweh. This is a collaboration with Darius and our PhD advisor, Prof. Qingwei Nan. So future condition was introduced 1 year ago. It was introduced for the purpose of bug detection and program repair. So specifically, the bugs we are catching are some general types of bugs like memory usage or resource leak, non-pointer dereference, or more general bug type called unchecked return values. So there's an example of how we write future conditions as a specification. So future condition, we write for certain APIs that you want to reason about. For example, for malloc function, it will allocate heap memories. So the pre-post condition says that the input value size should be positive, and there's two possibilities on the return value. Either is a non-pointer or a non-pointer. And for if the return value is not null, then we will trigger an event called malloc with the argument of the return pointer. And in the future, we can describe the constraints saying that when the return value is not null, then remember finally to free the return pointer. So as we can see, future condition provide a way to write user-defined specifications for the important APIs. And it can capture the constraints after the certain function call. And it combines arithmetic constraints and linear temporal logics. For example, globally, the operators like globally, finally, next, etc. It enables modular reasoning, which means that each function is only reasoned once, and when it's being called, that it can be replaced by its verified specification. With that, we can also have lightweight specification inference. As you can imagine, if we have a specification for malloc, that we can infer the specification for the functions which make use of malloc. However, there are three critical limitations that from the previous work that the solution for entailment checking is sort of inefficient. And since it focuses on bug finding over soundness, which means that they can drop paths and can do strengthening of the program states, it does not have a formal guarantee that there's no missed validations. And because of this focus, it handles loops via unrolling. So therefore, this limitation also motivates this work that for the rest of the talk, I will explain to you why these are limitations and what are our technical contributions. With that, there's an example showing here. This is a use after free bug recorded from the CWE website. It has 3 buffers and have a sequence of operations on those buffers. So you start from mallocing for buffer 1 and 2 and free the second buffer. And at some point, we have a use after free bug here at line 7. The reason why it is a use after free is that the argument used in string copy as a destination of some content was freed earlier before it's being used. So we like to use future condition and the reasoning techniques to detect such bugs. For that purpose, we define the specification for malloc, free, and the string copy. I have already explained the definition of the specification for malloc. So there's another future condition here introduced for free statements, which says that for the input pointer, once we freed it, then globally do not make use of this pointer anymore. And then the post condition of string copy triggers an event which makes use of the first argument. So we can imagine the combination of the future condition of free, which triggers from line 5, and the events which emitted from line 7 would capture this bug for us. And then it made use of a reasoning rule when we have function calls. So this is the extended version of Howard-style verification for function calls. When we have function call, we retrieve the specification for this function. And the difference is that earlier we only checked the precondition that the current state entails the precondition of the function call. But now we will need to check that the execution, the behavior after this function call actually satisfy the future condition of the current function. With that as a guideline, the reasoning looks as follows. So when we have the first malloc, we trigger we have the first proof obligation, which says that finally free the first buffer. And then the left-hand side is just the rest of the execution trace, including mallocing buffer 2 till the last statement of freeing the buffer 3. And indeed, the first entailment check should go through because we have a witness in the middle of the trace saying that the buffer 1 is indeed freed. So the first entailment check succeeded. And this process go on till when we have the first free statements on the buffer 2, and it triggers a future condition that globally do not make use of this buffer 2. And then we find that for the rest of the trace, that the statement of string copy at line 7, this event violates the constraint we had that it actually made use of buffer 2 at this point. Therefore, we captured a bug by a failed entailment checking. Okay, before that, so this process looks somewhat inefficient. So informally, it looks a bit of a quadratic complexity with respect to the number of future conditions that we trigger along the way. Because, for example, the free statements at the last line had to be checked 5 times for this simple program. So we propose a new solution for reasoning about future conditions, which to guarantee that each line of the code or each event emitted from the code is only being analyzed once. So the solution is to embed the future condition constraint into the program state and propagate it along the way. So at the beginning, we start from a simple program state, which has existential quantifiers over the program variables, and have empty trace. Epsilon stands for empty trace. And then the future condition field is underscore star, which means it allows anything to happen in the future. But when we have the first malloc function, that the trace has been extended with 1 event, and also the future condition is being added with 1 constraint that finally we need to free this first buffer. And the process goes on, we extend the events, extending the future conditions with the conjunctions there. Till that, we observe that at line, we had a future condition here that finally freed the buffer 2. And when we actually free the buffer 2, this constraint has been resolved into underscore star, which means that we no longer need to look for the free for buffer 2 already. The obligation has been fulfilled. And it continues to add more future conditions into the state. Till the moment that when we had a string copy event emitted, that by subtracting the string copy event from the future condition constraint, it leads to a false. So the error message says that subtracting this event from this future condition leads to the false. So this is very easy for us to know that which future condition has been violated and why. So as we can see, we have achieved a linear trace processing that each event is only being processed once, indeed. And this is achieved by embedding the future conditions into the program state and manipulate the states using trace conjunction and subtractions. For that, we have achieved the first goal, which is to have a more efficient entailment checking, which has the linear complexity by reasoning about the future conditions. Now we show that how are we going to handle loops. So this is a false negative example shown in the previous work, that we are recursively malloc 5 pieces of heap locations into the array, but we only free the head of the array. So this would be a memory leak because we have malloc from 0 to 5 location of the memories, but then we only free it once. However, this will not be detected from the earlier work because it unrolls the loop exactly once. So if you unroll it, we will see, the analyzer sees that there's only one piece of memory being allocated, and indeed it's being freed by the end. So there is no memory free. There's no memory leak. However, we would like to capture such bugs so that to remove the false negatives. So the solution is that we can now provide the specification for loops via predicates of bags of future conditions. So now we not only can, instead of saying at the certain location of the memory that we have this future condition, we can provide a bag of predicates which captures a bag of elements which share the similar future conditions. So for example, here, the predicate has two arguments, have an iterator I and has a bag. So this is a bag of contents that for each of the elements in the bag that we need to free it at some point. With this specification, when we reason about the main function, when we call the malloc n, this will instantiate the predicates with a concrete bound, which from 0 to 5. So the bag is concrete now with elements 0 to 5. And then when we free only one of it, the subtraction will give us a residue which says that predicates now, the future condition is only contained from 1 to 5, as in the first element is being freed, so we don't need to capture its future condition anymore. And also correspondingly adding the globally do not make use of the first elements of the array into the future condition. In that case, by the end of the program, we will have an error message here saying, because it's the end of the program, the empty trace will not satisfy the obligation which to free the elements from 1 to 5. That's why that's how we capture this bug. And more importantly is the method how are we going to verify while loops. So this is it's similar to the traditional Hard logic verification rule for the loops, which we need to find the invariant which holds at the beginning of the loop, also holds by the end of the loop, and we can conclude the state with the invariant conjunct with the negation of the loop guard. The difference is that we have extended the program state from arithmetic constraint and traces with a future condition here. So when verifying this while loop, we will need to find the invariant of this loop which captures the predicates, which captures the behavior of the loop. So the syntax here is very similar to Daphne, that the invariant says that exists the iterator I, that for each iteration that so the predicate holds from the location 0 to I. And by running through the one iteration of the loop, we will be extending, when we have a more malloc here, we'll be extending the predicate first. And by the loop, we'll also increment the iterator, so that we'll also increment the value of I as well. By the end, we retrieve the same predicate with increased value I. So we say that the invariant holds by the end of the program. And we conclude that by the end, I is being greater or equal than n, and in this case, we can be more precise that I will be exactly equals to n. That's why we concluded this predicates by the end for the specification for malloc n. And the invariant is supposed to be provided by the users, and in this work, we provide very lightweight inference synthesis for such invariants as well. So now we indeed have a mechanism to write the recursive predicates for the loops which manipulate resources. Last piece, we're trying to have a soundness formalization for the proposed verification work, that it is sound defined as follows. So the soundness the formalization has been constructed by the following three parts. That the first one is we define an instrumented semantics for the target language, which says that is a big step semantics from a given program E, when it evaluates the concrete value V, it changed the concrete program state stack and execution trace to the primed version. We also define a semantics model for the trace specifications, as in what does it mean by saying that a concrete stack and a concrete execution trace satisfy a given assertion with respect to the traces. And also we have a set of forward verification rules, which is the main contribution for this work, that which manipulate the future conditions and capture the violations along the way. So the soundness is defined, this is a definition of soundness in ROC, that it says if the verification system conclude a valid triple starting from a precondition, pre-trace, pre-future condition, and concludes a post-condition Q and a post-trace theta2, and a concluded future condition. And then if the concrete state, stack state S1 satisfy the precondition and the execution trace at the beginning, row 1 satisfy the trace, the theta 1 at the beginning, and the big step semantics also transform the transform the concrete state S1 row 1 F1 into S2 row 2 F3, and with the concrete value V here. In that case, it indicates the concluding value satisfy the post-condition Q. The concluding trace satisfy the concluded trace specification theta 2. And very interestingly is that the future condition concluded by the forward reasoning result has to entail the future condition concluded by the big step semantics. The interpretation of such an entailment is that it is only sound to strengthen the future conditions along the way so that we do not miss any violations. So I find it interesting because usually for verification works, we are allowed to over-approximate the program states, but in fact, it's only be sound if we only strengthen the future conditions along the way. Okay. So we have got a soundness definition for the verification work as well. So I'll briefly go through the experimental results. We have found a bunch of APIs in different scenarios. For example, for the file operation, open, close operations, thread usage, when we create it and you create a lock, you need to check the return value. Memory usage, socket usage, you need to close it. Database usage, and the general unchecked return value and non-pointed reference. So these APIs are found from the GitHub repository and as well as CWE websites, which captures all the common pattern of the bugs. We have done our experiments on around 1,600 plus lines of code. For that, we wrote 34 predefined specifications for the APIs. And then the tool can infer the specification for around 100 functions, which is the total number of the functions we taken in this experiment. It also inferred around 20 loop invariant, and the expected violations were 51, and we have reported 55 of them. So indeed, there is no missed violation, and they have false positives. And the false positives is allowed in the verification setting, but the cause of it would be the limited expressiveness and sometimes the weakening of the program states. There are case studies of those cases in the paper. You can check out more there. Right. So to summarize that, is to draw a comparison of what we have done in this work and the previous work is, so both of them are targeting at a compositional reasoning for temporal properties. And both of them employs lightweight specification inference. The difference is that the earlier work is focused on the under-approximation setting that you can drop paths whenever the path is getting too many. However, in this work, we can only over-approximate, so to weaken the program states when a path explosion happens. And obviously, there's a different treatment of the loops. One via unrolling, the other one via recursive predicates, but at the sacrifice that you need to provide the loop invariant. Since the earlier work doesn't need to write this invariance and can drop paths, of course, it's very suitable for large-scale usability. You can just run the analyzer, and whenever it's become too big, you drop paths. Whenever there's a loop, you unroll them. So it can target at a large-scale programs. However, in this work, we guarantee there's no false negatives because it is sound by design. And as I explained before, earlier work is also fast and mostly automated. But in this work, we try to improve the efficiency of the entailment checking. Okay, last point is that this work is more suitable for conservative analysis for critical systems which you do not want any miss of violations. And both of them can share the future work that so far we have got no machine checkable certification. All the proofs are done by the automated tool. It's not machine checked. And it can enhance the expressiveness, as the first speaker in this session mentioned, that we can extend it to hyperproperty, but you need to think about how to deal with the trace subtraction for hyperproperties from there. With that, this is the end of my talk. Thank you for listening, and I'll be taking questions.
Okay, many thanks, Yahweh, for the presentation. So we have a bit of time for questions.
How do you relate this to separation logic?
Yes. Okay, the direct answer is that the trace abstraction is simpler than separation logic. And we indeed compare with, so technically the difference is that for separation logic, when they capture memory errors, it will run the tool, and by the end of the program to check whether the program state has residue heap allocation. In that case, they detect the memory leak, right? So we do similar things. We do for the same purpose, but use different ways using the trace representation and the linear temporal logic constraints to capture such violations. So the a more high-level difference is that this work is more targeting on the properties which can be represented as temporal constraints, and the memory violation is just one of it. For example, you can also describe things like this location of the memory has to be freed within 2 steps. Such things that this cannot be, these are temporal aspect, right? So it's very unique using temporal logic, which may necessarily can be achieved by separation logic. That would be. Thank you very much.
Okay, maybe one more very quick question. So you mentioned you have formalized forward reasoning rules. Did you look into backwards reasoning? So it's very interesting here because what you have here is a trace abstraction, not a state abstraction. So would it make sense, or would it actually work for your set of predicates to try to look into backwards reasoning, to have maybe something about necessary precondition or sufficient precondition, and to try to prove programs this way? Did you look into this approach?
That's a good question. I saw many mainstream tools are using backwards reasoning. I haven't thought about it. However, I think the main difference or the difficulty for me could be the how do we capture the loops when you do backwards reasoning, that to propagate a precondition, a necessary precondition to satisfy the post condition. This would, so maybe there's difference there, but I don't need to worry about that now. So.
Thank you very much, fair enough.
Thank you very
okay,
much.
so thanks again for the presentation. Now going to move to the fourth presentation of the session, which is about contextual equality saturation by Alexandre Drouvery, Thomas Jensen, and David Pichardy. And Alexandre is going to give the presentation. Good.
Does everyone hear me? Can you hear me okay? Yes, wonderful. So hi everyone, thanks for attending this talk. I'm Alexandre Drouvery, I'm a PhD student from INRIA Rennes, and today I will present to you contextual equality saturation. So in one sentence, it's extending the technique known as equality saturation to better reason about programs using the conditionals in said programs. So before delving in, maybe I will present to you what is equality saturation through an example. So the main idea is equality saturation is automated reasoning on terms. So So you have terms, maybe n plus 1 minus 1 and n, and you want to show that they are equal or equivalent. And your main tool to prove that terms are equal are what we call rewriting rules or equivalence rules. It allows you to say that certain forms of terms are equivalent to other forms. For example, any term of the form x plus 1 with x any term is equivalent to something s of x. So you are able to characterize many types of equivalence using this. You can characterize, for instance, the associativity of plus and minus, the fact that 0 will be the neutral of plus. And how we will use those rules through equality saturation is as follows. We will load our terms in what we call an E-graph, which represents equivalence classes of terms. So here you have minus, plus, n1, 1, and here you have n. In dashed lines, you can see equivalence classes of the terms. Right now, every term is in its own equivalence class. And my goal is to fuse this class up here and this one using my rules. So let's apply a rule. We see that we have n plus 1 in our E-graph, so we can apply the first rule. X plus 1 becomes s of x. So we add to the E-graph s of n in the same class as plus n1. So the main thing to remark in here is that this is a rewriting that is non-destructive. The old E-graph, this one, is still present in the new E-graph. So by applying my first rule, I didn't lose any opportunity to apply other rules. And so I can saturate the E-graph, enrich it with as many information as I want by applying every rule I can anywhere I can. So I will skip a few steps until we reach some form of some conditions that satisfies us, which is n is in the same class as or minus term initial. So to summarize everything I said to you, equality saturation performs rewriting on terms in the theory of congruence closure. It is parameterized by a rewriting rule set. And the general idea is you apply every rule you can, everywhere you can, until you are satisfied. It works on the shoulders of a powerful data structure called an E-graph, which encodes equivalence classes of terms. And it is very efficient in enabling rewriting. You will, if you have a rule, you will know where you can apply it and how you can apply it. So more precisely, we can do automated reasoning with equality saturation. We can also do automated program reasoning. So in 2011, Tate et al. Showed that you could design a term language to represent programs, and specifically the input-output relations of programs as terms. And therefore, you could reason about them using rewriting rules, using equality saturation. So this is powerful as it enables many applications, such as optimization. You have an initial program. You want to find an equivalent program that is more efficient in a way. Program analysis. And what interests us today, equivalence checking. So let's get into the problem that interests me precisely. I will want to validate some kinds of program transformations of a specific form. I want to correlate bodies of such form, x greater than or equal y to x greater than y. These two are not equivalent, but they are equivalent inside the check that x is different than y. So this is the form of program I want to correlate with this one. You can imagine different, maybe stronger transformations. This is the one I will use in this presentation. So I want to characterize this relationship. So I will design a rewriting rule that I will use in my rule set to characterize this equivalence. And so to design this rule, I will consider the simplest possible program that match this form, in which inside the check you have only x greater than or equal y and x greater than y. So if I look at the E-graph that represents these programs, the terms representing this program, they look something like this. You get in here your greater than or equal xy, here greater than xy. Here's a check that x is different from y, and here you want to prove equivalent those phi terms, which I will explain now. So phi is a special type of term introduced by Tate, which allows to represent ternary conditional expressions, something that is sometimes wrote like this in the C language. The first child is a condition, and the second and third are the then and else branch. So if we look at a simple example, if x equals 5, then y becomes x plus 2, otherwise y becomes 6. It can be represented by the following terms. Phi of x equals 5 If so, x plus 2, otherwise 6. This is the output of y for the following program. So using these phi terms, I can design rewriting rules. So if I want to encode, as said before, this equivalence between a ternary conditional expression, if x is different than y, x greater than or equal y, another branch that doesn't interest me, and the same ternary structure with x greater than y, I can encode it using a rewriting rule, using my phi symbol in here. And this rule can be applied to prove exactly that this term is equivalent to this one, the above I showed you earlier, which is good. So this rule works. I can prove, this is what is done to prove in standard equality situation relationships between conditional programs, programs that rely on conditionals. So that's good, but there is something more I want of my rules, which is a form of universality. I want them to work on a variety of different programs. And here this one works on the simplest possible program matching my pattern. So let's consider a slightly more complex program. So you have the same general structure, ternary conditional expression, but the then branch is a bit more complex. You have your check x greater than or equal y, and you do the conjunction of it with a Boolean. So can I apply my rule in here? You will see that the different ingredients are here. There is a phi, the different forms, the greater than or equal. But actually, the rule requires that the second child of the phi term has the form term x is greater than or equal term y. This is not the case in here. This hand in here is blocking me. So you can deal with it, classically, by swapping the phi and the hand using an auxiliary rule that encodes some form of distributivity of phi over hand. So for something like this, phi of a condition C, x and y, z, can become the hand of phi cxz, phi cy true. You can check that if C is true, in here you get x and y, and in here you get, if it is false, you get z and true, which is z. So the rule is sound, it works. If I use it, I can swap the phi in here and the hand in here, and then I can use my rule. But it has a bit of problem. In general, these rules are called swapping rules. They do not scale. They pollute your rule set in a way that you need one rule per operator, and they lengthen your proofs. So earlier, I wanted to apply one rule, but to do so, I needed to apply an auxiliary rule. My proof is now twice longer. And remember that in equality situation, I will apply every rule I can, everywhere I can. So if my proof is twice longer, this gives me more opportunities to apply irrelevant rules in other parts of my graph, and therefore it will tank my performance quite a lot. So can we do away with swapping rules? So this is the core of our contribution, which is a new type of rewriting rules we call contextual rewriting rules, which define what we call contextual equality situation. So let's look at a contextual rewriting rule. You still get a general idea of writing a pattern into another one, but the pattern you get in here is slightly more complex than earlier. The pattern is divided between a contextual pattern, a check that must be made, and then you get the structural pattern, x greater than or equal y, which is the one you want to replace by the right-hand part of the rule. So what this rule encodes is the equivalence of these two structures. If you do a check that x is different from y, and then in an arbitrary then branch of this check, you have an occurrence of x greater than or equal y, you can replace this whole structure by a similar phi term with the same arbitrary then branch, but you have replaced greater than or equal by greater than. So this is a new type of rule entirely, which means I need to define how I will apply them in my graph. Equality saturation will work with them. So how can I find occurrences of a contextual rule in my graph? Well, a specification of how to do so could be to look for what I call contextual sources, so checks that my contextual patterns hold, phi of x different than y. And then I could do a traversal of the then branch, looking for my structural occurrence, x greater than or equal y. And then to apply the rule, now that I have found an occurrence, a path from a source to the occurrence, to the structural occurrence, sorry, I can copy this path below a new phi term, but at the end of the path I will replace my greater than or equal here by greater than. So this general specification allows me to solve the above problem of trying to apply my contextual rule in one step in my graph in here. So of course this specification is a bit naive. The core of our contribution is actually optimizing the specification with algorithms in order to apply contextual rules efficiently. And the key factor in equality saturation is what we call fail fast. Very often in a large E-graph, you will have no occurrence whatsoever of your rule before you do some other steps. And so we need to be able to quickly find that there are no occurrences of a contextual rule. The way we do so is with a new system of what we call E-graph annotations, in which phi terms in here will annotate the then branch with annotations that indicate that a path from a contextual source of x different than y exists above this class. The generality is that the annotation also allows you to find efficiently the path that exists. And so imaging looking for occurrence of your rule can now be done by looking for the structural occurrence and then checking in the annotation if or not a path exists. So if you want more details, you can find more in the paper, including algorithms on how to maintain these annotations, because an E-graph is a dynamic object. We will enrich it with new information, so we need to adapt our annotations to these enrichments. And you will also find details about the complexity analysis and an experimental evaluation that we made available in our artifacts. So a word about this evaluation, maybe. We made a prototype of equality saturation that implements both standard strategies and the contextual strategy we detailed in here. We tried it on synthesized benchmarks of increasing complexity to solve. Maybe the source is increasingly far from the target. Maybe you need to apply standard rules before you can apply your contextual rules. And we found that overall, contextual equality saturation was about 30% more efficient than the standard swapping rule-based approach. So in conclusion, we supplemented equality saturation with information from conditional propagation analysis, and we found it worthwhile for both expressivity, what you can say with your rule set, and efficiency. So there are future works possible on this, both these axes. On the side of expressivity, you could use the results from other static analysis than conditional propagation. And on the side of efficiency, initially what motivated us was building an equivalence checking tool for a specific translation validation from Java language to Kotlin language. So we could now implement this technology into such a tool. Thanks for listening.
Okay, thank you. Okay, so we have a few minutes for questions.
So I was just curious, so SMT solvers make use of eGraphs and they also do like backtracking, trying different paths. So are there any applications of this to SMT solvers?
Oh, what you just said is eGraph are used in SMT solvers?
Yes.
I'm not a bit of an expert in SMT solvers. Not on the top of my mind.
Oh, okay.
Yeah, you could get a back and forth. We are using SMT solver technology for other ends, but you could figure a back and forth with what we figured in here back to the SMT. I could see it, yeah. Thanks.
Okay, so please.
Hi, so you have equality saturation with context now, so the obvious thing is bindings. Can you get bindings?
What do you mean by bindings?
Like variable bindings in the rules of equality saturation.
Oh, okay. Usually when the program representation we use...
Say you want to manipulate lambdas, right? Lambdas that bind variables.
Oh. Usually our term representation does away with variables. We no longer have any reference to them.
But you're adding context, so maybe you can have a better representation.
Oh, okay, that's an interesting idea.
Okay, thanks.
I don't have much to say about this, sorry. Thank you.
Thank you for the great talk. I would be happy to hear a little bit about the implementation details for this.
Yeah?
Oh.
About the implementation?
The implementation details. How you implemented it in code.
Okay. So I guess now we use the standard. We implemented an e-graph in general, but now we have an e-graph is supplemented with a map that maps each class towards an annotation table. Each class can have multiple annotations, and this annotation is also hash-const for better efficiency. I don't know what other details you want. We could talk later, maybe.
No, that's it. Thank you.
Thank you.
Thank you. So thanks again. So maybe while we are swapping laptop, I think Barry wanted to ask a question. I mean, maybe quickly.
Another question?
Switching laptops, maybe.
My question is how this work relates to conditional rewriting.
Okay. As in directly in the program, you would rewrite conditions?
Well, there's in the rewriting community, there's been a substantial amount of work on conditional rewriting, and perhaps your work is built on top of that, or better or worse. I was wondering if have you made a comparison?
Not on the top of my mind, but I would say my work is more built on top of this.
Right. Okay.
Thank you.
And we are now moving to the last talk of today's last session for SAS, which is about abstracting concolic execution for soft contract verification. So this is work by Bram van den Bogaert, sorry, Quentin Stevenard, and Cohen de Rouver. And Bram is going to give the presentation. So please.
So